Manufacturing Day at Tennessee Tech. We are happy to have attendees from over 15 countries around the world join us for this event. My name is Michelle Davis, and I am the coordinator for the Center for Manufacturing Research at Tennessee Tech. The CMR was created to draw together resources of the state of Tennessee, the university, industries, and government funding agencies into a cooperative effort to be on the leading edge of the latest technological advances in the manufacturing field. Additive manufacturing is a focus area of the CMR, and several of our faculty, associates, and students are actively doing research in that field. You will be hearing from some of them today. We also have presenters from other universities, research labs, and companies talking about their cutting-edge work in additive manufacturing. Some housekeeping notes. The presentations are divided into 5 areas: additive manufacturing with cement-based materials, multi-material additive manufacturing, wire arc additive manufacturing from the United Kingdom, and AM potpourri. To keep on schedule, we will not have live questions and answers. Instead, we invite you to submit your questions via a Q&A form that will be posted in the chat box, and I will forward your question and contact info to the presenter, who will follow up after the presentations are over. We will also be recording this event. I'd like to acknowledge Dr. Joe Bernanke, Dr. Duc Bong Kim, Dr. Ying Zhang, and especially Dr. Ismail Fadan for establishing Additive Manufacturing Day at Tennessee Tech. We look forward to holding this event annually. Now I'd like to introduce Dr. Jennifer Taylor, who will be kicking things off. Dr. Taylor is the Vice President of Research and Economic Development at Tennessee Tech. Dr. Taylor?
Thank you, Michelle. It is my pleasure to welcome you all to our first annual Additive Manufacturing Day here at Tennessee Tech. I looked over the program. I think you all are in store for a wonderful day. It sounds very exciting. And I just wanted to send my welcome and wish you all a wonderful day. Thank you.
Thank you, Dr. Taylor. We will be starting in just a couple of minutes. Thank you. Okay, we'll go ahead and get started with our first presenter. The title of the presentation is Chemomechanical Properties of 3D Printed Cement Paste. And the presenter is Florence Sanchez and Michael Cosson of Vanderbilt University. Thank you.
Can you all see my slides?
Yes.
All right, good morning, everyone. My name is Florence Sanchez. I'm a professor in the Civil and Environmental Engineering Department at Vanderbilt University. My research focuses on the chemomechanical behavior of materials, and For the past 4 years, my group has been working on 3D printing of cement-based materials. So I would like first to thank Tennessee Tech for organizing this Additive Manufacturing Day, and in particular, Professor Joe Bernacchi for asking me to introduce the session on additive manufacturing with cement-based materials. As you know, concrete is a rather pedestrian material, not commonly associated with high tech. Yet, concrete is one of the most used materials in the world, with several billion tons of concrete used every year around the world for a wide range of applications. So I wanted to take a few minutes to talk about the remarkable advances in cement and concrete technologies that we have had over the past 50 years. Cement-based materials have become increasingly more complex. We went from compressive strength that were about 20 megapascal 50 years ago to now over 200 megapascal. With nanotechnologies and the development of nanoparticles and nanotubes, concrete can have multifunctional properties such as self-sensing or self-cleaning or self-healing properties. Concrete has also become more sustainable with the use of a wide range of supplementary materials, the use of nanomaterials, but also the development of innovative alternative binders. Other advances have been with the development of coatings and the use of short fibers, reinforcement, to improve the durability. So the question is 3D printing the next revolution for cement-based materials and the construction industry? 3D printing has received significant interest by the construction industry in the last few years. 3D printing eliminates the need for formwork. Molding and formwork represent 35 to 60% of the cost of a concrete structure. So 3D printing can reduce the construction cost and time. It also eliminates the time for spent on rebar replacement and inspection, and in turn can increase productivity and safety. And of course, it provides flexibility in the construction and architectural freedom that cannot be obtained with traditional casting. In addition, 3D printing also provides a more efficient use of materials. You can place now material only where you need it, and that eliminates also waste. So 3D printing can significantly reduce the large environmental footprint that is associated with construction. So these are the benefits for the construction industry. But there is another aspect that is probably less evaluated, that is the new paradigm 3D printing provides for cement-based materials and design approaches. 3D printing has created a new opportunity for concrete to optimize the binder and to use other type of binders and local materials. So 3D printing provides an opportunity for controlling locally the microstructure and the interface between the reinforcement and the materials, and also to realize a hierarchy of structures and patterns with much greater control and over a broader range of length scales. So 3D printing provides the ability to design 3D printed elements that have tunable and unique or enhanced property that are not achievable with the current casting. So in that context of opportunity of the binders and to develop novel material, Vanderbilt, Tennessee Tech, and Purdue University started a few years ago a research project on 3D printing of civil infrastructure materials with controlled macrostructural architectures. And this project was funded by the National Science Foundation. The goal of the research project was to better understand the interplay between chemistry, the hydration kinetics and rheology of the printing media, and the solidification of the printed filament, and how all of this integrates with the layer by layer successive deposition and the interface between layers. Another aspect of that research was to determine the effect of printing media formulation and hierarchy of structures and patterns on the mechanical response of the printed materials. So the next presentation that we are going to see this morning are some of the results from that research and collaboration from the different groups at Vanderbilt, Tennessee Tech, and Purdue University. And I'm now pleased to introduce one of my graduate students, Michael Cosson, who has been working on the aspect of 3D printing for cement-based materials development. Michael is going to talk about the chemomechanical properties of 3D printed cement paste.
All right, thank you for that introduction, Florence. Just give me a second to share my slides. Can everybody see my slides and hear me okay?
Yes.
All right, as Dr. Sanchez mentioned, I'm going to be talking about the chemomechanical properties of 3D printed cement paste. And this is the work that we did at Vanderbilt University as part of this collaboration with Purdue and Tennessee Tech. So the goal of our aspect of the project here at Vanderbilt is to determine the effect of the extrusion process and how building these structures up layer by layer affects the mechanical properties of both the 3D printed filaments and then the structures built at a multi-scale level. So the way we do that is by using a feedback between our 3D printing, using the variables that we can control, including the water cement ratio and admixtures, etc. And using a feedback with the information that we gain by using different types of characterization methods. And we're doing that at multiple scales. So we're testing the mechanical properties at the macro scale, as well as at the micro scale using nano indentation, and then using that information to inform microstructure and phase assemblage using predominantly SEM and EDS. So for this talk, we're going to be talking about some of our results with nano indentation results, as well as some of our multi-scale mechanical results using carbon microfibers and carbon nanofibers as internal reinforcement for 3D printed filaments. So for this project, we're primarily using this machine that you see here on the right. It is a commercially available printer, and we're printing mostly at a smaller scale compared to what you'll see in some other projects, with a filament diameter of 1.6 millimeters. While there are some downsides of this, the primary advantage is that it gives us more precise control over the printing process, allowing us to have more careful control over what material is placed where, for a closer control of the hierarchy of the structures and the patterns that we're printing, so that we can use that information to more closely develop novel materials and printing processes. I'm not going to go into too much detail about this because I know Dr. Bernanke's students have several talks talking about this, but it's important to understand that you can't just 3D print with any old cementitious material. It's important for it to be workable enough that you can use it to form filaments, and buildable enough, it's important that it's workable enough and then buildable enough that it can hold its own weight without deformation of successive layers, while also having enough open time so that it is in the fresh state long enough for you to extrude your structure that you're printing. And then once it's printed, it also has to have adequate hardened material properties for whatever application is being used for in the industry. There are a couple considerations that are important to take into account when you're extruding a cementitious material, particularly with the propensity for it to segregate during the extrusion pressure. So there's a couple dynamic processes that occur during this process. Water can be driven out of the extruded filament into a lubrication layer to facilitate plug flow, which can change the availability of water within the filament, while simultaneously you can be driving water from the bulk cement paste into the filament as it's printing, which can have a converse increase of the local water availability within an extruded filament. So it's important to understand that small changes in your printing conditions can have significant impacts on the availability of your water within your paste, and that this is a very important effect that needs to be considered when you're designing materials and processes for 3D printing with cementitious materials. So what we found is that when you're printing with what we call a neat paste, which is our paste, which has a cocktail of admixtures in it, but no internal fiber reinforcement, is that you get this watery surface layer that's caused by the water being driven out into a lubrication layer, as I mentioned, to facilitate that plug flow. But one very important thing that needs to be considered, and what we found when we printed with carbon nanofibers, is that if you use an internal reinforcement or an internal material that is hydrophobic, it can add to that driving force with the extrusion pressure so that you get more water coming out of your printed filament, and you can have a thicker lubrication layer, which can lead to under extrusion, as you can see here in the middle picture on the right, where the filaments are printed much thinner and you get significant gaps between your filaments. Another consideration when you're using larger fibers, such as the carbon microfibers we're using here in this bottom image, is that they will have a tendency to preferentially align with the direction of the extrusion. But if they don't preferentially align properly, which is prone to happening occasionally, you can see a blockage in the fibers and have occasional printing discontinuities, such as this picture here on the bottom. So when we were printing with the carbon microfibers, as I mentioned a second ago, we saw that they preferentially extruded in the direction, preferentially aligned in the direction of extrusion, which when we printed in a rectilinear pattern where every layer was offset 90 degrees from the previous layer, produced an effect where you had an alternating directionality of the printing pattern. So in this picture here on the right, you can see that in the left half of this cutout, there are fibers that you can see pretty much everywhere, and they're difficult to see, but you can see they're circled in the cutout on the right. Whereas on the right, the only reason we can see the fibers at all is because we have a pore here, which allows us to see further into the image plane, and all the fibers are parallel to the image plane. And that's compared to the cast where the fibers were all aligned. But interestingly to note, other than that, as we've tried to study the interface, there's no other obvious indicator that there's an interface being crossed here. So there's only really very minimal microstructural changes associated with the interface between these printed filaments. Another important thing to consider was that we saw that there was a non-uniform dispersion of the filaments, of the fibers throughout the filaments, and it's thought that as you sort of have these fibers align or not align, but not quite enough to cause a blockage, you can have fibers that have a tendency to come out sort of all at once. So as for the effect of this reinforcement strategy on the mechanical properties, what we saw was that for all three of our inks that we're talking about here, the neat reference ink, the ink with the carbon nanofibers, and the ink with the carbon microfibers, there's a reduction in compressive strength between the 3D printed compared to the cast. We found that this reduction was the biggest for the carbon nanofibers, which we think has more to do with that under extrusion process and having less of a well-formed structure as compared to the actual reinforcement provided by the carbon nanofibers. Relative to the reference cement ink with the microfibers, we saw an increase in performance, both with an increase in ultimate failure strength, as well as interesting post-yield behaviors, where you can see in the image on the right, after it reaches that primary strength, rather than failing right away, we see what's called post-yield strain softening behavior, where the structure doesn't pop and fail, but rather fails gradually and less catastrophically. When looking at the influence of the extrusion on the micromechanical properties of the individually printed filaments, what we find is that you get sort of two types of filaments. You get filaments with low mechanical properties or filaments with high mechanical properties. And that's not usually consistent with the direction of the printing. So what we found is when we casted samples with different water to cement ratios, we got this sort of similar effect, whereas you have a higher water to cement ratio, that corresponds to a reduction in the mechanical properties of the filaments as measured by nanoindentation. So what we found was that for the low mechanical property filaments, we get this similar effect to what we're seeing when we're casting with a higher water to cement ratio, whereas with the high mechanical property filaments, we're getting something more similar to what we're casting at a lower water to cement ratio. So that suggests that what we're seeing as we extrude is that there's a big change in the availability of the water within the structures, and that's changing the mechanical properties of those filaments once they've been hardened. As far as the effect of this on the microstructure, what we found is that there aren't big visible changes in the microstructure between these low mechanical property filaments and the high mechanical property filaments. And that suggests that most of the changes are more at the nanoscale and the pore structure and then the packing density of the individual chemical hydration products, as opposed to changes within those hydration reactions themselves. We do see, however, that there is some evidence of changes in the dissolution depending on the chemistry of the unhydrated particles. So I'm not going to get too deep into that for this talk. When we look at indents when we separate indents using EDS by their chemistry and then only look at certain hydration products, we're looking here at calcium silicate hydrate gel, which is one of the most important hydration products for a cement material. What we see is that even when you sort for the chemistry, you're still seeing those big changes in the mechanical properties between the low mechanical property filaments and the high mechanical property filaments. And that's still mirroring what we're seeing in the samples cast with different water to cement ratios. So that further supports our hypothesis that it's being driven by water availability, but also that these changes are being driven more by changes to the mechanical structure rather than the chemistry of the hydrated products. So in conclusion, there are some very important things to be taken into account when you're printing with a small filament diameter, including that liquid phase filtration can change your local water availability at the extrusion point, and that these changes are dynamic and can change both your mechanical and your chemical behavior of your printed filaments at multiple scales. And then the interactions between the paste constituents during the extrusion really also needs to be considered, as we saw with the carbon nanofiber hydrophobicity leading to under extrusion, and with the carbon microfibers aligning with the direction of the print, as well as water being transported through our filaments during printing. What I want to leave you on is the thought that we can sort of use these interactions to tune the mechanical properties of our structures for the specific application that we're using them for. So with that, I would like to acknowledge our funding sources, and I invite you to please reach out to us if you have any questions. Thank you so much.
Thank you, Michael. Thank you, Florence. I'd just like to remind you that if you have questions, we have a Q&A form in the chat box. Our next speaker will be Babajide Onanuga of Tennessee Tech University on the rheology of cement-based paste.
Thank you, Michelle. Good morning. I hope everybody can see my screen.
Yes, we can.
Okay, thank you. Yeah, so thank you. My name is Babajide again, and my advisor at Tech is Dr. Joseph Benaki. And I would like to acknowledge our collaborators at NIST for their contribution. So my work is on rheology of cement-based printing paste. Cement-based printing paste is a particulate suspension and a reactive material that hydrates with water. Rheology is the study of how liquid or soft solid flows, and the rheology of cement paste is important to its printability. The question for me is about controlling rheology. What really affects rheology control for printing applications? And my work is really a fundamental study on rheology under shear conditions. And the study is motivated, again, by printing. So what I'm showing here is a poor printing object and a good printing object. And the key difference between the two is rheology control. It is the same particulate material. It's just that the dispersive media is vastly different. So what is my approach? I looked at the rheology for two particle types, but in three different dispersive media. One which is water, and the other two, 0.15% super plasticizer and 0.15% ammonium polymethacrylate, in order to study rheology as a function of the two additives. So we compare a non-reactive surrogate to reactive cement. We chose silicon carbide as the material because it is imminently inert, and compare it to cement particles. And we made sure that the particle size distribution, at least for some base conditions, were the same. And the reason why I'm using silicon carbide is because I'm trying to isolate the factors that affect rheology. And I want to know how much of a factor hydration is in the first 120 minutes under shear conditions. So I'm trying to understand the effect of additives on rheology and how much of rheology under flow conditions is contributed by hydration and how much is particulate driven. And so our base condition was a dry size powder particle size distribution. So we manufactured the silicon carbide until the silicon carbide distribution looks like cement, as seen in the graph. The result shows that both solids were remarkably alike, as seen by the overlap of the two curves. So shown here is the effect of organic dispersing agents on the apparent particle size distribution. The addition of both organic species altered the apparent size distribution when compared to the apparent distribution in deionized water. Superplasticizer clearly disperses both solids, and it breaks up floc when you compare the blue and the golden curves. Whereas ammonium polymetacrylate tends to apparently flocculate cement, it has no effect on the silicon carbide in low dose when you compare the red and the blue curve as well. So now let's discuss rheology even further. One way to study the flow of cement paste is through rotational rheometry, where a small thin film of material is placed between two parallel plates, and one of the plates is pinned, usually the upper one. And when you do that, you generate a flow curve, the plot of shear stress against shear rate. And for Newtonian fluid, regardless of whether one is increasing or decreasing that spinning rate, that fluid behaves exactly the same along a straight line. The shear stress depends only on the shear rate. But if the shear stress is a function of how long a fluid is sheared, then that fluid is said to have time-dependent behavior. The two forms of time-dependent flow behavior are thixotropy and anti-thixotropy, or negative thixotropy, or rheopeptic fluid. So what is the quick difference between the two? The behavior is thixotropy. When the down curve during the decreasing spinning rate, the black curve, falls below the up curve, the red one, in a ramp up and ramp down loop experiment, as seen in the first loop on your right. The reverse is anti-thixotropy, which results when the down curve lies above the up curve, as seen in the second hysteresis loop. So let's discuss cement rheology. The rheology of all cement paste was characterized by a transition from thixotropy to anti-thixotropic behavior in the first 5 cyclical loops. And the thixotropic behavior is typical of a flocculated system, while anti-thixotropic behavior indicates an eventual deflocculated cement paste system. So the stable rheological condition of Portland cement paste under shear is anti-thixotropic, not thixotropic. Also, the thixotropic or anti-thixotropic loop area is a measure of the power per unit volume, that is the time rate of energy storage per unit volume. And as you can see, upon transition, the area inside the anti-thixotropic hysteresis loop is larger for paste in deionized water than the other two doped paste. And this indicates that both agents seems to reduce the anti-thixotropic energy storage. And this is caused by reducing frictional interaction. So how does the particle size distribution and zeta potential measurement impact rheology? Dispersing agents do two things: modify the particle surface charges and the apparent particle size distribution. And in fact, changing both in different directions may have competing impacts on rheology. So what did we learn? Although the electrostatic charge on cement particles doesn't change with superplasticizer, as seen on the bar graph, the apparent size distribution reduces by half, indicating that superplasticizer sterically disrupts flux. Secondly, while ammonium polymetacrylate clearly changes the surface charge in a direction that should favor deflocculation, but in fact, it doesn't. And the apparent particle size increases by more than double. Nonetheless, the rheology suggests that in fact, ammonium polymetacrylate has a lubricating effect, apparently. And once the paste begins to be sheared, it behaves as a flocculated material and transition to antithixotropy. Here I briefly compare the rheology of cement against that of silicon carbide. In the first 45 minutes of mixing, while cement paste transits from thixotropy to antithixotropy, silicon carbide paste transits from antithixotropy to an unstable mixed mode thixotropic and antithixotropic behavior, attributed to their different initial conditions of structuration immediately after mixing. Also, results suggest that flow curves for cement paste in the ammonium polymetacrylate, wherein hydration is occurring, evolve to a similar value of shear stress when compared to the silicon carbide. Same comparison is true for both solid, even at longer times of up to 120 minutes, suggesting that the difference in the time evolution of the hysteresis curve under flow conditions is not due to hydration alone, since silicon carbide is a non-hydrating system. What here is the maximum shear stress attained in each cycle loop against time for both paste in the two liquid treatments. And we see that both paste evolve to similar shear stress values. So what are the broad conclusions to be made in this study? The stable rheological condition of Portland cement paste under shear is antithixotropic, not thixotropic. With the comparable rheology observation for non-reactive silicon carbide paste and reactive cement paste, it is difficult to suggest that changes in cement flow rheology in the first 120 minutes after mixing are the effect of hydration rather than particulate interaction. And finally, although certain additives in dilute systems significantly alter the apparent particle size distribution of particles in suspension, that observation alone cannot be used to produce predictable rheological outcome. Thank you.
Thank you, Babajidi. Our next speaker will be Hajar Tahiri from Tennessee Tech University, and her presentation is titled Hydrogels, a Transformative Technology for Cement-Based Printing Materials.
Thank you, everyone. My name is Hajar Tahiri, and my today's presentation is about hydrogels, a transformative technology for cement-based printing materials. And I'm working under supervision of Dr. Bernanke at Tennessee Technological University. So what we are doing at Tennessee Tech, we are working on rheology of cement-based materials that Babajide Onanova already talked about it. I am using hydrogels in cement-based printing paste. And Abdussalam Mohammed is talking about 2D stationary computational printing of cement-based materials. Habitat for Humanity reports that 1.6 billion people live without adequate housing. So might additive manufacturing be a solution? The answer is yes. Researchers in the United States and abroad are actively working on additive manufacturing technology that might soon make it possible to house the world's growing population in an affordable, adequate housing. But yet, there are a number of critical hurdles. The material must be extrudable. It should be able to retain its shape once deposited. The deposited layers should not collapse under the load of subsequent layers, and a good bond strength between the layers must be ensured for better hardened properties. Our results shows that unadmixed cement paste is simply not printable. So what's the solution? The answer is additives or admixtures that can be added to the cement paste to make it printable. We are searching for effective additives, and there are lots of candidates. There are traditional admixtures like superplasticizers or off-the-shelf viscosity modifying agents. People also are using fillers like clays and limestones and supplementally cementitious materials like ash, slag, and silica fume. There are also less traditional admixtures such as hydrogel forming polymers. There are some issues and problems with typical admixtures, which are including bleeding and water migration during shearing, jamming of the 3D printer, mechanically unstable behavior of these materials when they shear, and chemically unstable behavior of these materials at high pH of the cementitious materials. So we are looking for admixtures that solve these problems. We selected hydrogel forming polymers because of their properties, and we decided not to go with traditional admixtures. So which hydrogels and why hydrogel forming polymers? Because hydrogel forming polymers can have high viscosity. They can be very shear thinning. They don't need to be thixotropic. They can retain water and act as internal curing aids. They can be very lubricating. So hydrogel forming polymers have wonderful properties for possibly being candidate materials for producing those robust, scalable, printable pastes. Therefore, after screening a number of candidates, we selected 3 hydrogel forming polymers that were also stable under shearing and stable under high pH of cementitious materials. These hydrogels were hydroxyethyl methyl cellulose, hydroxypropyl methyl cellulose, and polyethylene oxide. So here you can see the procedure, the pathway that I used in order to select hydrogel forming polymers. But even for the hydrogel forming polymers, our results showed that not all of the hydrogel forming polymers give us good printability outcomes. So our work is based on understanding how to choose and identify appropriate printing aids. We have our experimental design included 4x4x3 factorial design. We varied the gel to cement ratio, and also we varied gel percent, and we printed based on benchmark hollow cylinder object based on the 3 hydrogel forming polymers. As you can see here with the naked eye, that as we are moving from right to left or from polyethylene oxide to hydroxyethyl methyl cellulose, the domains of printability improved and the quality of the printability improves. We can clearly see that we have domains of unprintable materials, that the material simply didn't come out of the nozzle. We also have domains of very well printed objects and domains of poorly printable materials. So in order to understand this, why some of these behaviors happen, we performed gel and paste rheology. Here I bring for you typical example of gel rheological measurements of hydroxyethyl methyl cellulose. You can clearly see in the left side the flow curve of hydroxyethyl methyl cellulose, and as you can see at all of the concentrations, the hydrogels are shear thinning, and the viscosity improved and increased as we increase the gel concentration. We also perform the oscillatory measurements of the hydrogels. You can see here as we increase, as you can see here, except for the 8% of the gel, for all of the concentration, we have a yield point that the material transition from solid-like to fluid-like behavior. But as we are moving from 4% to 8%, we no longer see the transition from solid to liquid-like behavior. We also plotted here the gel storage modulus versus the polymer content. As you can clearly see it here, as we increase the gel concentration, the gel storage modulus increased, whereas for the ratio of the loss modulus to the storage modulus, the ratio decreased. We also performed some paste rheological characterization. I plotted here for 2 different gel to cement ratios at different concentration or at 3 different gel percents. Here you can see that as we increase the gel percent, the paste storage modulus decrease, which is in reverse with the relationship of the gel storage modulus. So we wanted to correlate these results to the printability outcomes. Here in this graph, which is a complex graph, we superimpose the rheological information of the gels in the left side of the graph and the paste storage modulus inside of the graph. As you can clearly see it here, as we increase the gel concentration, the gel storage modulus increased, and the printability improved. Whereas as we increase the gel concentration, the paste storage modulus decreased, and also the printability improved. Furthermore, as we increase the gel to cement ratio, we see that the cement paste storage modulus decreased and the printability improved. So we can say that as we increase the gel concentration, gel stiffness increased, the paste malleability increased, and the print fidelity increased, which you can clearly see that as the gel concentration increased, gel storage modulus increased, and the paste storage modulus decreased, and the printability improved. So all in all, hydrogel forming polymers were found to transform unprintable neat cement paste into a highly robust printing media. The highest performing printing paste had malleable characteristics and retained rheologically solid-like behavior. Printability increased proportionally with increase in neat gel storage modulus, but inversely proportional to the paste storage modulus. By increasing the gel concentration, the stiffness of the gel increased, which increased a malleable paste, and ultimately the print fidelity increased. And thank you for your presentation.
Thank you, Hajar.
Thank you.
We'll move on to our next speaker, who is Abdul Salam Muhammad of Tennessee Tech University, and his talk is entitled 2D Stational Computational Printing of Cement-Based Materials.
Thank you, Michelle. Good morning, everyone. The objective of this study was to link relevant experimental rheological measures of printing paste to actual printing outcomes and computer-generated 2D printed constructs. Therefore, an efficient computational strategy was developed for modeling additively manufactured cement-based materials, which captures the dynamics of 2D slices at stationary location along a print path, that is 2D stationary computational printing. Now, this work revolves around a particular experimental design where I have 7 water to cement ratios of cement paste, which are neat cement paste without any admixtures. So there are 2 pathways. There is a modeling path where I use experimental flow data to gather or extract yield stress, plastic viscosity information that is needed to put into constitutive models. Then there is a separate validation step. Then I do computational printing and produces a computationally printed object that is compared to the second pathway where I actually print the object, I section them, I photograph the cross section and make the comparison between experimental and computationally printed object. Now to show how my experiment was done, I basically hand mix water and cement for a bit. I then shear it at low shear rate for 30 seconds and then at high shear rate for an additional 30 seconds. And that paste is ready, and I called it cement paste A, and I print with it immediately. But as a second path, I let that paste age a bit for 30 minutes. I shear it again and I called it cement paste B, and I immediately print with it also. So I'm trying to see if there is an effect of aging on the cement paste in terms of print quality and my ability to actually predict printability. Now I take these two cement paste A and B and I immediately measure the rheology of it and establish these flow curves. Now these flow curves were developed in a particular way where I pre-shear the material in accordance with a certain recipe in order to deflocculate the particles, and then I gather the down curve from 200 inverse seconds down to 0 inverse seconds, and I called it the data set that I need. I then fit that data set with either a Bingham model or a Herschel-Buckley model, and I get these beautiful fits with Herschel-Buckley model for most cases, except for maybe this one case where it was rather stiff paste and it turned out to be Bingham than Herschel-Buckley light. That being said, I collect these experimental data, I do it in triplicate, and I determine the yield stress, plastic viscosity, and the fit exponent for both cement paste A and B. Bottom line is, when I plot yield stress versus water to cement ratio, I see these two beautiful curves with the aging effect. So if we age for 30 minutes, the material is rather stiffer than the material that is not aged. However, for water to cement ratio that is above 0.4, there is really no effect of aging for a period of at least 30 minutes. So what I have already did is I made the paste, I did the flow rheology and extracted the yield stress, plastic viscosity, and the dimensionless fit parameter for like Herschel-Buckley model. But to understand how the rheology of cement paste work, a good test is to do a slum flow test. The slum cone is a simple device. It is conical, which is filled with the cement paste, and the cone is lifted such that the cement paste slumps under gravity. So here I did the experimental slum flow test and compared the experimental outcomes with constitutive model outcomes. So here is the comparison of experimental and simulation results of mini slum flow test from 0.325 water to cement ratio all the way up to 0.5 that are in good agreements with the experimental results. Now I need to compare the 3D printed object to see if I can actually predict the morphology of the printed objects instead of the slum cone. So I prepared our paste, again both paste A and B, and I have actually printed object that is a double wall hollow cylinder. And then on the other pathway, I'm doing 2D stationary computational printing, and then I'm going to bring them together for comparative analysis. So these are the actual objects that I printed, which is very small, on the order of 27 millimeters tall by 36 millimeters in diameter. I show a range of objects here from 0.3 to 0.375 water to cement ratio, some printed and some collapsed in between. If I go to water to cement ratio as high as 0.4 to 0.5, the cement paste slumps completely and it won't print at all. That being said, the question is, how can I move from modeling a single gob of material to actually modeling printing? So what I do is, if you imagine that you can only see what happens in this plane AA, this plane is just slicing through some bit of space where the printer is going to pass periodically every now and then. The first thing that you would see is that the first layer will be deposited at time T1, but it won't be until sometimes T2 that the printer will come back over that layer and deposit the second layer. So at time T2 minus T1, the first layer will slump on itself because it's Portland cement. At time T2, the second layer will deposit such that at T3 minus T2, not only the upper layer will slump on itself, but the bottom layer will slump under the weight of upper layer. At time T3, the printer passes again and it deposits the third layer and on, and it will continue to. Now I have prepared a video that shows how does this happens computationally. So what I'm not doing here is piling up a bunch of layers at time t equals 0 and then slumping all of them together. That's not what this is. So these are the stack of layers that are going to be printing a double wall. The double wall because we are printing a double wall hollow cylinder. So the printer is coming past the outer layer and the inner layer, and the material is wicking and slumping into it. I selected a particular object here that will fail at some point because I wanted you to see that this 2D technique, although it is two-dimensional and computationally very efficient, it can actually capture the dynamics of a failure. And in a bit, you will see that there is a collapse of the wall. So here is the collapse of the wall. So here you see the comparison of cut cross section of actual printed object and computationally printed object, which are in good agreement for cement paste A, as well as for cement paste B. At high water to cement ratio, computationally printed object also predicted the collapse or failure similar to actual printed object. Now to establish a more quantitative comparison between the model-based prints and actual printed objects, a 2D cross-section based print fidelity index was calculated by overlapping the actual printed object or computationally printed object with the idealized object. So this is an idealized object and this is a computationally printed object. So first I align the basal plane and then I align the axial centroid. So here I penalized for anything that is outside the idealized object and anything that is not covered inside the idealized object, and measured the print fidelity index from 0 to 1, where 0 is worst or not printed at all and 1 is the perfect object that matches the idealized object. So here I plotted the print index of actual printed object on the yield stress versus water to cement ratio graph. And you see that as the water to cement ratio decreases, the yield stress increases and the printability increases. Thus, the printability moves from low print fidelity domain to a high print fidelity domain as the paste water to cement ratio decreases and the yield stress increases. Now, if I plot the model and actual print index 1-on-1, I see a strong near linear relation. And if I put the yield stress on it, I see that the good printing outcome was observed at the printability index of 0.7 or greater. So this shows that at printability index of 0.7 or greater, that is a yield stress of about greater than equals to 237 Pascal is required to produce good printing outcomes. So in conclusion, the 2D stationary computational printing concept produces printing outcomes that correlates well with experimental 3D printing outcomes and link rheological properties to printability of desired shape at a given scale. We have submitted these findings in cement and concrete research, and we also have a paper about scaling rules for 3D printing of cement-based materials. Thank you.
Thank you, Abdul. Our next speaker is Riza Moini of Princeton University, and the title of the presentation is Design and Additive Manufacturing of Architected Cementitious Materials.
Good afternoon, I suppose everybody. We're on the Eastern time, so it's almost afternoon. Happy to be here. Thank you for inviting me for this talk. So for the short amount of time that we have, I'll try to go over the few topics very broadly, just to cover what has been accomplished and what are some of the future directions. On design and additive manufacturing of architected cementitious materials, I'm Reza Moini. I'm an assistant professor in the Department of Civil and Environmental Engineering at Princeton University. So about 2016, as mentioned by Professor Sanchez, collaborative research started together with Tennessee Tech and Vanderbilt University, Professor Sanchez and Professor Bernanke, in which we touched on a number of different topics. As you know, additive manufacturing has been around now for a while, and it exists across multiple scales. Early on at the smaller scale and prototyping, and later on towards more structural elements and components, and then more recently towards full-size structures for home building, but also for renewable energies. But there are several aspects that it's a multidisciplinary, multifaceted topic. And so on one side, we worked on the design opportunities, ability to print materials in different shapes and forms, whether in terms of exterior topologies or interior architectures, enables you to achieve compliant mechanisms like that. But there are also challenges, as was discussed by Michael earlier, in terms of the heterogeneities that results from these layer interfaces. So we looked at some of the microstructural aspects. In terms of materials rheology, the past two presentations covered interesting work on the rheological challenges of formulating materials and failures. And on the fracture side, once you have a structure, then you have to worry about the fracture and damage mechanisms in these systems. So early on, we focused on design opportunities, combining really materials and space. In a monolithic material, you're dealing with inherent properties of the material. You apply the force in a brittle system, the material fails. In an architected material, you have the ability to tune the response by tuning the architecture and then perhaps improve some of the properties. So we looked into a number of different architectures, as you can see here, but more specifically, I'm going to very briefly talk about these Boolean and Helical architectures in which, as you deposit the materials in a layer by layer fashion, you continue to rotate the orientation. So inspired by mantis shrimp and the ductile club more specifically, we looked into the role of pitch angle or the rotation angle at which you orient the filaments in the subsequent layers to see if we can investigate the design parameters and can we fabricate them and can we characterize them in terms of their tensile properties. So what we found was that as you see in the, if I can get my laser here, as you see, the gray chart is the cast as opposed to everything else is 3D printed helical architectures. What we found was that we could improve the work of failure or the toughness of the material without really sacrificing the strength here. And we further looked into the microstructural characteristics after damage. So if you look at this structure, this element that has an 8-degree pitch angle, in this orientation, what you find is that there are two toughening mechanisms that contributed to improve toughness in these solid systems, one of which is crack deflection at the interface and subsequent interfacial cracking. There was also an overall crack twisting, which was challenging to trigger, which is challenging to trigger in a brittle system that we also observed. So together we inferred that controlling the architecture and tapping on the challenge of weakening interface, you could combine them together to improve material properties. In terms of going back to the microstructural heterogeneities, we looked into microstructure of 3D printed cement paste at two different scales at about 30 and 4 micron resolution. What we found was that there are macropores that happens throughout the printing process due to inconsistency, but there are also microchannels that are essentially trapped air in between the filaments. There are two other discoveries that we had in terms of filament rearrangements from a straight path, but also these bright regions, which later we found through a smaller scale characterization that are nothing but accumulation of higher degrees of unhydrated cement grains near the pores, near the microchannels. And so we clearly understood there is a homogeneous core versus a porous interface. So we looked into a smaller scale resolution, and what we found was that these microchannels are actually connected through one another in micropores, which was evidence for the presence of a weak interface. And then we also noticed the rearrangement from some type of a diamond shape, microchannel to a triangular shape, which is visible in the video. So we later quantified these in terms of using a method called K-means clustering, and compared them to the reference cast. So the 3D printed samples typically not only had higher degrees of porosity volumetrically, but when we did the segmentation, we noticed that the arrangement or the morphologies are also fundamentally different. As you can see here, the porosity induced by printing is distinct in the blue, the printed samples. We have macropores, microchannels, and micropores, whereas in the cast case, you have a continuous spectrum of porosity. Then we focus on the damage mechanisms in these samples. As in cast, there was no distinct crack pattern, just localization of a crack in form of a shear cone, as opposed to I can get this video to run, as opposed to a helical architecture in this case, where we observed numerous microcracking at the interface and a helical exterior crack pattern. So in other words, we were able to distribute the microcracking similar to those we observed in the flexural test, but here we're looking into compression, which we later found helped also improve the toughness of the material, intrinsic toughness of the material, compared to the cast counterparts. The curve right, let me get my there again. The graph right here is comparing the area under the curve between the cast and the Boolean architectures. The last part of the talk I would like to focus on is the rheology and buildability. Many of that was broadly discussed in the past two presentations. So there are two main failure mechanisms with 3D printing of soft materials: buckling at the lower layers, yielding at the lower layers as opposed to buckling and the top layers. And what happens is that from accumulation of geometrical imperfections, you typically, as was shown in the previous work, you typically end up with additional bending moments and accumulation of eccentricity, which then leads to local buckling and then global buckling. And the question is, which rheological properties is responsible for buckling specifically? You first have to overcome extrudability, then you have to overcome the yielding at the lower layers. Once you're able to print an object, then buckling is typically the common failure mechanism. So it's important to identify what rheological properties needs to be controlled. So for that, we looked into the correlations of buildability of hollow cylinders with different rheological properties. And what we found was that all three shear moduli associated with elastic properties or stiffness, G, G star, and G prime, demonstrated a stronger correlation with buildability as opposed to yield stress, and G double prime. And so, in other words, buckling in 3D printed soft materials is mainly dependent upon stiffness. And as you can see here, viscosity essentially controls the ability to extrude. Yielding controls the ability to avoid yielding failure. Once you build up, you really should be looking into the storage modules or complex modules to control buckling. Although these properties are interrelated, it's an important distinction as we scale up the processes in the construction as a mean to tune the chemical characteristics of surfactants and other chemical admixtures specifically for 3D printing. We also looked at an isosceles triangle as a mean to kind of come up with a quantitative way to assess the deflection of single filaments. The test helped us look at the ability to span over varied length and help characterize the amount of deformation in a neat cement paste as opposed to a cement paste with a high range water reducing admixtures and viscosity modifying admixtures, which were all quantified using micro CT. We would like to thank NSF for the support for this work, Purdue College of Engineering and Life School of Civil Engineering, but also our collaborators at NIST, RCAM, Vanderbilt, and Tennessee Tech. So going forward, my lab works on a number of different areas, bio-inspired designs, multifunctional materials, and will continue to advance the robotic manufacturing and autonomous systems. Here are some of the more recent activities we've had in the lab with 3D printing concrete of larger scale Boolean architectures and Cellulose. Some of the ongoing research projects going forward is really looking into some of the durability issues and fracture issues that has been overlooked. And hopefully we can contribute to some of those aspects for the community, but also looking into some of the polymer additives for 3D printing cement-based materials. I would also like to thank my group that have helped put some of these videos together. And with that, I'd like to thank you all.
Thank you very much. This brings us to our next topic area, which is multi-material additive manufacturing. And our first speaker is Ankit Gupta, development of novel biocompatible material for fabricating 3D printed composite dentures.
Affordable. So today I'm going to present you some possibility of creating the patient-specific and the affordable composite dentures using desktop 3D printers. So let me discuss about something about additive manufacturing first, just to give you a general idea. As we all know, additive manufacturing is a technology to create the three-dimensional structures to build the material layer by layer in the layer by layer format. Simple. So like suppose you have one idea and you have to transform it into a real form. So I can say that 3D printing is the best way to do that. 3D printing helps to create the three-dimensional structures in a very cheap way and in the light format. So composite material, let me discuss something about the composite material as well with you. So composite material is just a combination of two or more materials to get the good properties, better than the individual components, better than the two materials which we are using. So how these two materials mix? These two materials generally don't dissolve and they just merge together completely to get the high strength, high stiffness, and the combined low density. So now let me discuss about fiber reinforced additive manufacturing. So this is a technology I use for creating the dentures. See, I discussed with you the additive manufacturing. I discussed with you the composite material. So what I did in my research is I combined these two technologies. I took the flexibility of additive manufacturing. I took the advantages of the composite material. I combined them and created the composite dentures. And we all know like single material cannot fulfill the needs of all the applications. So we have to do the composite printing. So for those applications, fiber reinforced additive manufacturing comes into the picture. So I use that for creating the composite dentures. Now I will tell you why additive manufacturing is so important to the field, why it is important for the dentistry field. As you can see from the plot, 3D printing in dentistry is growing exponentially and forecast to become a 3.1 billion industry in 2022. And in 2020, it holds a market of $2.2 billion. And it is growing at the rate of 26%. Now, if I talk about the worldwide manufacturing, it is a $15 trillion industry, and it holds the 16% of the world economy. So that's why I can say that additive manufacturing is very, very important. So let me come back to the topic. Like now I will discuss with you how to create the composite dentures, how to create the affordable and patient-specific dentures, to be more specific with you. So there are some requirements I set for creating those dentures. So denture produced should be highly accurate, lightweight, and structurally durable. And it should be, the surface quality of the denture should be very, very good with improved clinical properties. Clinical properties, I mean to say about mechanical, thermal, and the biological properties. It should be of low cost because it should be affordable by any patient, and it also reduces and eliminate the short and long-term health risks. Let me tell you, let me start the procedure, how I created the composite dentures. For creating the composite denture, I created my own material. I created my own composite filament. The benefit of you creating our own filament is that you can create it in a very cheap way, and you can also control the fiber behavior. Means you can control the fiber length, you can control the fiber distribution, you can control the fiber breakage. You can play with those things, because fiber behavior is very, very important in judging the final clinical performance of the composite dentures. So now I will discuss with you how I created those composite dentures, composite filament. So first I took the two different materials, short glass fibers and the PMA pellets for my research. Then I dried them in a furnace for 7 to 8 hours to get rid of the moisture. Then I poured them into the extruder to create a uniform diameter composite filament for the composite denture production, and to use that composite filament inside the 3D printer. See, I created the composite filament. Now I have to check whether the two materials I took, right, to create the composite filament. Now I have to check whether these two materials are compatible to each other or not. Should I go with those two materials for creating the composite dentures or not? Okay, so accordingly I did the microstructure analysis. So as you can see from the structure analysis, the fibers are well distributed inside the matrix material, and there is insignificant gap at the interface of the matrix and the fibers. From these two conclusions from the microstructure analysis, we can say that these two materials are good to produce the composite dentures. So this is the entire experimental procedure for creating a composite dentures, as I discussed with you before as well. Like how I did that, I just took the two different materials, mixed them thoroughly, put them in the furnace, dried them for several hours, and then put them into the extruder to create a uniform diameter composite filament. And then I use those composite filament to do the 3D printing of the composite dentures. It's a very cheap way to produce a composite dentures, but in that way you can produce affordable and patient-specific dentures with high surface quality. Now I will show you the research outcomes of that. So there are some examples of dentures I printed with low-cost desktop 3D printer. There are some dentures with pure material and some with the reinforced materials. So as I told you, the main requirement of the composite denture is like it should be of good surface quality, it should be of high strength. So in order to get a good strength, I varied the glass fiber percentage. I increased the glass fiber percentage to get a good strength. In order to get a good surface quality, I lowered down the layer while 3D printing. That so that I can get a good surface quality print. And I got that. Here are some examples of the prints I got from the low-cost desktop 3D printers. And this is the way I printed the desktop, the composite dentures. I printed the dentures all in the vertical direction in order to avoid the support material. Because if you're not printing the support materials, ultimately you are saving the material and ultimately you are saving the cost. Ultimately, you will get the low-cost composite dentures. So I printed all the dentures in the vertical height. Then after that, I did some microstructure analysis to see the fiber behavior inside the composite dentures. As you can see from the microstructure analysis, the fibers are well distributed inside the composite in the matrix material, which ultimately enhance the clinical performance of the composite dentures. See, now research outcomes I want to discuss with you. See, I am creating composite dentures that I have to use in the mouth. This patient has to use in the mouth, and he has to bite as well. He has to bite the food with those dentures. So there are various forms of stresses that occurs while chewing. One can be tensile, shear, and compressive. So accordingly, I tested all the properties, all the strength, like tensile strength, flexural strength, compressive strength, to check what is the final clinical performance of the dentures. So I did some tensile property analysis. The maximum strength I got is maximum tensile strength I got is 73 megapascal, which is more than the standard requirement for any denture available in the market. Then I did some flexural analysis. The maximum strength I got is 151, which is twice as the standard requirement for the dentures. Then I did some compression analysis. The maximum I got is 93 megapascal, which is higher than the standard requirement for the dentures available in the market. Now the surface roughness, I told you, like we are creating composite dentures. It should be of high strength. It should be of good surface quality. Surface quality because it is important because we don't want it to be it should not create a discomfort in the mouth of the patient. So I did some surface roughness analysis and I figured out that you can see from the data, the surface roughness varies from 5 to 7 microns, which is very, very less. So we can say that the dentures we created with low cost desktop 3D printers are of very, very high quality. See, the main reason for our research is for creating the dentures is the cost. We have to create the affordable dentures. So accordingly, I did some cost analysis, time analysis, and the weight analysis. As you can see from the data, the cost of the dentures created by low cost desktop 3D printer is $1 to $2. And the weight varies from 17 to 20 grams, which is very, very less. So here I can conclude that the dentures which we produce from the low cost desktop 3D printer, we can save 60% of the weight of the dentures available in the market, and the cost we got is 92% reduction in the cost for the dentures available in the market. So a conclusion, I can say that like the dentures produced are highly accurate, affordable, lightweight, and structurally durable. The dentures produced are of good quality with improved clinical performance. Acknowledgement, I really want to thank Center for Manufacturing Research, Additive Manufacturing Research and Innovation Laboratory, University and Australia Dental Research and Foundation for their support for this project. So thank you so much.
Thank you very much. I would like to remind you that for questions, we have a Q&A form in the chat box. And our next speaker is Ziqing Zhang from Tennessee Tech University. Quality analysis of low-cost metal material extrusion fabricated parts using machine learning.
Thank you so much. Thank you everyone for coming to my presentation. My name is Zhicheng, a PhD candidate in Department of Mechanical Engineering of Tennessee Technological University. Dr. Ismail Fida is my advisor. The topic today is quality analysis of low-cost metal material extrusion fabricated parts using machine learning. My presentation will start from the research background to the introduction of the manufacturing process, the current results, application, and conclusion. First, the research background. What is additive manufacturing? Additive manufacturing is a layer-by-layer manufacturing process. It is also known as 3D printing. Material extrusion is one of the most widely used additive manufacturing method. In this catalog, the filament will be melting out and reform the part on the printing bed layer by layer. And the low-cost metal material extrusion is a very new developed metal material additive manufacturing process. Why do we need to develop these techniques? Because in the material extrusion process, the filament should be melted out, but it is impossible to use pure metal to do this, because the melting temperature of most metals are much higher than the working temperature of the 3D printer. For example, the melting temperature of the bronze is around 900 degrees Celsius, but the working temperature of most 3D printers are lower than 300 degrees Celsius. So we developed these new techniques. In this technique, the physical parts are built in with composite filament consisting of metal powders in a polymer matrix. After the additive manufacturing process, the part will be centering to have the pure metals. For example, we generated the models on the software to get the G code and do the 3D printing as usual. But after the 3D printing, we have a sintering process. After the sintering process, the final part is a pure metal. For example, in this research, we use a bronze PLA material to do the manufacturing. The first is the STL file generated on the SolidWorks, and we get the G code to do the 3D printing on the middle. This is a non-centered part. It's a mixture of bronze and the PLA. And after the sintering process, the final part is a pure bronze. The PLA is melting out in the sintering process. This is a sketch of the sintering process. We see that the melting metal powders in a plastic matrix. We increase the temperature from the room temperature to a sintering temperature. The sintering temperature is a little lower than the melting temperature of the metal. For example, the melting temperature of the bronze is 900 degrees Celsius. So our centric temperature is around 890 degrees Celsius, just a little lower. And in this process, the plastic is melting out and the metal powders gather together to form the final part is a pure metal. But at the end of the final part, it has some internal void. This cannot be avoided. This is some real examples. The left is the non-center samples. We can see the bronze powders, the light in the PLA matrix. After the centering, the final part is pure metal, pure bronze, but we have some internal void here. By changing the parameter manufacturing, like the layer thickness, the rack ratios, the centering temperature, we could minimize the size of the internal void, but it cannot be zero. In this research, since this is a very new techniques, we just measure 3 mechanical properties, which are dimensional accuracy, surface roughness, and the microstructure or percentage of internal voids. The dimensional accuracy is the shrink ratio of the final parts compared with the design parts. The surface roughness, we use RA numbers because it's the most widely used one, and we measured by a SG 210 surface roughness tester. And the microstructure, we compare with the theoretical mass and the real mass. The difference between them is the percentage of the internal void, because the void does not have any mass. And before the manufacturing process, we could use machine learning to do predictions on the final results after the manufacturing to change our manufacturing parameters to have good quality final parts. We use machine learning to do the predictions, and 2 machine learning algorithms are used in this research, which are support vector regression and the neural network. In the neural network, we have multiple hidden layers, so it's a deep neural network. These are the machine learning prediction results. The top graph is a learning curve. I put the learning curve here. It just shows that we already have enough data because of the training errors and the validation errors merge at the end, and the bias is not big. So small bias, small variance, it's a good fit. It's not overfitting, not underfitting. We have suitable number of data to do the prediction. And the evaluation matrix of the results, we use mean square error. The mean square error of the machine learning predictions on the dimensional accuracy and the microstructure is almost 0. It means it's very accurate enough to use in the real world applications. However, for the surface roughness predictions, is not that good. So in the next step, what we want to do is just minimize this mean square error of the surface roughness predictions by the machine learning. Also, we use response surface methodology to find the best manufacturing parameters in the low-cost metal material extrusion. For the optical processing parameters for the best layer thickness, if we want to have a small internal void, the layer thickness should be around 0.1 to 0.15 millimeters. But if we want to have a very good surface roughness, the layer thickness should be around 0.2 to 0.28, 0.27 millimeters. So in the real world applications, if you want to have a very small internal void, minimize the layer thickness. If you want to have good final results of the surface roughness, just increase the layer thickness. And for the centering temperature, the good news is that between the range of 285 to 295, all 3 parameters are in a good range. So we could use centering temperature between this range. I'd like to say that this is the results of bronze PLA material. If you use another material, you need to do more research, cannot just use these numbers. And the applications, this is a very, very new techniques. It does not have any applications now. So our group generated the rock arm on the car engine. On the left is the non-centered parts after 3D printing, and on the right is the final parts after centering. This is very hard, and it's applicable in the car engine. So it means this techniques is applicable in the real world. The conclusion: first, the preliminary research have shown that low-cost metal material extrusion could be used in the manufacturing process. Then the dimensional accuracy and the percentage of internal void predictions by the machine learning are accurate enough to use in the real-world applications. And number three, by using the response surface methodology, we could find the most suitable manufacturing parameters to get a good quality final results. And I'd like to thank the Additive Manufacturing Research and Innovation Laboratory of Technical University and my team. Thank you so much.
Thank you, Ziting. Our next speaker is Seymour Hasanoff from the University of Alabama in Huntsville, and his presentation is titled Mechanical Application of Functionally Graded Composite Parts Manufactured by the Fused Filament Fabrication Process.
Hello, everyone. I'm Seymour Hasanoff. I'm an assistant professor in engineering technology at University of Alabama in Huntsville. And my topic today is the mechanical application of functional graded composite materials fabricated by the fused filament fabrication process. So let's get started. Okay, we already know that AM uses CAD data to fabricate objects layer by layer fashion as opposed to conventional formative and subtractive manufacturing processes. And AM is used for two main purposes. The one is for prototyping and the other one mainly used for real-time production. And additive manufacturing has 7 process categories. And today I would like to talk about one of them, which is the fused filament fabrication process. FFF utilize thermoplastics, composites, elastomers, and metal-infused polymer filaments to produce multi-material parts. In our research, we use a single nozzle extrusion process, which is overall called functional graded additive manufacturing. And FGAM intentionally modifies the processing parameters and gradually distribute materials within one component to meet the intended function. And here you can see the possible material combinations and the respective AM processes to fabricate functional composite parts useful for aerospace, automobile, and medical applications. So let's briefly talk about what is FGM. FGM are advanced engineering materials that presents complex, spatially varying material properties. And functional graded materials occur in nature as bones, teeth, and nature design actually these materials to meet their expected service requirements. And this idea is emulated from nature to solve engineering problems. And in these materials, the changes of material distribution contribute to property and functional deviations. And these are the examples of FGM occur in nature. And in engineering applications, FGM is used for a better adherence of dissimilar materials and used for a minimization of internal interfacial stresses between different or dissimilar materials. Here you can see an example of a tungsten copper FGM material that spatially changes its volume concentration and overall contributes to hardness and electrical and thermal conductivity or thermal properties of the final component. So these are some research literature that fabricated multi-material composites using additive manufacturing technology. And in the first image, you can see FGM ceramic composites with varying material concentrations. And the second one is multi-material ceramics 3D printed part using Cerafab multi-M3 3D printer. And the third one, you see that the combination of a lattice structure with functional gradation, which is produced at Lancaster University. And the next is multi-metal part and artificial intervertebral disc and sandwich plates and so on. And you can see the sandwich plate manufactured with a functional graded core using big area additive manufacturing in Oak Ridge National Lab. An interesting fact is that the cost, and you can see in the graph, the cost and the weight analysis showed that utilizing a gradient core can reduce the cost by 48% and the weight by 5%. So the Z-Morph 3D printer was used to fabricate multi-material structures with a dual pro extrusion head. And here's a schematic representation of that. And here we inserted the static mixer inside extrusion head to help mixing materials together. And ideally, dynamic mixer would blend material better. However, this is the future research needs to be addressed. And these are the sample parts fabricated by this technology. And this is the case study performed on the mounting bracket, a part fabricated by FFF technology with neat ABS and fiber reinforced ABS materials. And here we performed a numerical analysis first to identify the distribution of stresses under tension and compression loads. And first CAD geometry was created using SolidWorks software and then imported into ANSYS to perform static structure analysis, and which will help us to perform topology optimization. However, before performing this analysis, we need to define material properties for the entire part, which we'll talk about this in the next slides. Then material distribution was found using ANSYS topology optimization module. And in the next stage, we performed voxel design and segmentation method for the geometry, for gradient design, and tool path generation. And at the end, the part is ready for mechanical testing. So, okay, let's go back to see how we obtain effective properties of 3D printed composite parts, and I'll briefly summarize it. And here we perform a 3-scale homogenization approach to obtain effective material properties for ABS and carbon fiber reinforced ABS material. And the first scale is the micro scale, which consists of short carbon fibers and ABS matrix domain. And then the mesoscale, which is and some of our researchers talked about this, is its interbead shapes and with interbead voids. And this is created during layer by layer deposition process. And then the macro scale, a specimen geometry with gradient transition between materials was used in this research. And here you see the mounting bracket undergoes compression testing. And here we used 090 layup deposition process to get orthotropic material properties. And you can see the microstructural description over here, which will lead us to perform a homogenization process using RVE, representative volume element method. And you can see that the direction of fibers changes on the 0 and 90 layup direction. And this enables to do over here, so we perform a homogenization process to get an effective property for neat ABS and carbon fiber reinforced ABS materials. And overall, in this way, we can interpret the failure mechanism under tension and compression loads. And after performing stress analysis on microscale and mesoscale geometry. And this is the test setup for mounting bracket sample part, which undergoes tension and compression loads. And over here, you see FGM polycarbonate ABS and FGM carbon fiber ABS were compared with a material consisting of neat ABS materials. And polycarbonate ABS pair used for comparison purposes because it consists dissimilar material interfaces. And the first graph over here shows the compression test results, and it can be seen that one part has various compression response under the same loading conditions, which help us to design a functional composite parts with a tailored mechanical properties. And over here, you see the FGM polycarbonate ABS part also showed a 50% more load-bearing performance than neat ABS under compression load cases. And in the second image, you see the part under tension loads. And over here, FGM fiber reinforced ABS component demonstrated higher strength than other components because strength of neat ABS was increased by, let's say, incorporating short carbon fibers into high stress concentration areas. And overall results show that FGMs fabricated by the FFF, we can say low-cost process, FFF process inherited strength, stiffness, and toughness, which showed an improvement of overall material properties in comparison with the neat ABS materials. And I would like to thank you for your time, and please contact me if you have any questions regarding the topic. And you can also check our latest publication for more information and latest progress and challenges in this field. And I thank you, Dr. Fidan and Michelle, for inviting me, organizing such a great event. Thank you so much.
Thank you, Seamer. This brings us to our next topic, wire arc additive manufacturing. And I'd just like to remind you that for questions, we have a Q&A form in the chat box. The next speaker is Yusub Lee from Oak Ridge National Lab, Manufacturing and Prediction of Large-Scale Metal Components in Wire Arc AM.
Yeah, I'm trying to make a full screen, but looks like it doesn't work. Okay, so this is Yusub Lee, from Oak Ridge National Laboratory. I'm the R&D scientist in multi-scale the modeling group, which is in computational science division. So I mostly talking about the Oak Ridge National Laboratories and manufacturing demonstration facilities and then modeling and prediction effort for large-scale metal, the wire arc, and other metal AMs. So that is my collaborators and engineers and surgeon from Oak Ridge, and then there is the Professor Bong Kim from Tennessee Tech. He's my collaborators, and then I'm working with his student as well. So here I will do the very brief introduction of the Oak Ridge National Laboratories, who may not know about it. So we are located at the city of the Oak Ridge in Tennessee, and then we established 1942 as a part of Manhattan Project, and so we have lots of nuclear related facilities like graphite reactors and other things, and but those are transformed to scientific research. So we have really the high kind of top world top notch kind of nutrient facilities, and we are focusing on material sciences and also computer science and advanced manufacturing. So I am involved in the computer science and advanced manufacturing, those two part mainly. So then, there is the other kind of the Harding Valley campus at Oak Ridge. Those kind of Harding Valley campus consists of 3 buildings. So one is National Transportation Research Center and Greece Center for Batteries and Manufacturing Demonstration Facility, MDF, for additive manufacturing processes, which is on the right, the things. And then we have a couple of kind of core research and development, the areas to leverage the RNL science capability to solve challenges of industry partners. So we have like 20 to 40 new projects every year with the industry partners. Then we also publish 80 to 100 publication annually, and we are also heavily collaborating with academia, and so we have like 1,000 student internship since 2014. So also I have a student intern in a couple of weeks from Tennessee Tech. So then that's our collaborations. So MDF, we started with the electron beam melting machine. So in 2014, and then we have extended all the AM machines to like a laser powder bed and binder jets and a large scale, the arc welding, large scale laser metal welding, and then polymers and composites and other kind of parts. So then recently we have large scale metal AM. It's called Medusa, having 3 robotic arms, and then which is designed to make kind of the parts a lot faster and then have better accuracy things. So we have cross-cutting scientific disciplines. So that is large-scale metals and the metal powders and polymers and composites and hybrid AM, which means additive manufacturing plus subtractive manufacturing. So all those kind of the advanced manufacturings we are working on kind of the make a kind of closed loop system kind of by integrating these materials and simulation data analytics and characterizations and system controls. So each kind of the sections, many kind of step members are working on, and those kind of the development and researches is spread to and applied to the other systems. So then in this topic, I've tried to a little kind of more focusing on large scale meta AM, right? So we have many materials, and then we design toolpaths and then explore the many other materials like a 316 inconels and high temperature, low temperature materials. And also we develop these modeling capabilities, in parallel, the experiment, which is 7 feet tall kind of excavator arms, and then you will see the later. Okay, so then this is a kind of the Medusa system. So it has the 3 robot arms. Our goal is to kind of print kind of rapidly. So because the large part means it takes really long time, even for certain cases takes a month or a couple of weeks to complete the printing. So we need a really fast kind of printing speed. And also the large part means it has a kind of lot of problems in distortion and deformation, also mechanical properties. So we want to guarantee the part quality kind of by improving all the system things. So for that, we need feedstock development and simulation modeling, toolpath strategies, some mechanical simulations, and microstructure simulation as well to guarantee properties. And productivities, production rate, we need a lot of faster things rather than having one single touch. I mean, you easily think 3 robot arms make it kind of a couple of times faster in ideal cases, right? So, and then we also put some kind of sensors and data analytics, for example, IR cameras, speed cameras, and also we do the machine learning for this effort. And applications sure can be characterization, multi-material deposition, because it has 3 kind of feeders, right? So then we can do the multi-materials easily and data visualizations. There is a kind of those are the modeling effort we did, and so then our model is heavily validated with the simulation. I mean the experimental data for this one is laser scanned compared laser scanned data and predictions. You see it's a pretty good match, and also we have the hyper, the neutron measurement, and then so that is parallelly compared the simulations in qualitatively and quantitatively at various locations. Those are pretty good. And then yeah, so if you have any questions, then please contact me, Yusuf Lee, and thank you having me, Michelle and Professor Pong Kim and Terence Deck.
Thank you. Our next presentation is by Roman Hassan of Tennessee Tech University, Tailoring Microstructural Heterogeneity for Improved Mechanical Performance in Wire Arc Additively Manufactured Structures.
Good afternoon, everyone. I hope you can see my screen.
Yes, we can.
Okay, so I'm Roman Hassan. I'm a PhD candidate working with Professor Kim on wire arc additive manufacturing. So for today's presentation, the topic is the tailoring microstructural heterogeneity for improved mechanical performance in wire arc additively manufactured structures. So I will give a brief overview on the wire arc additive manufacturing process. So basically, wire arc additive manufacturing is based on welding technology. So we use welding power source, welding robots, and welding consumables to deposit in near net shape. So basically, the welding power source is used for melting the material, and the robots are through the robots, we control the deposition rate or the shape of the object. And in our setup, we basically have two kinds of power source. One is the GMAW or gas metal arc welding, and another is GTAW. So for this presentation, we'll be mostly focusing on the GMAW based system. So compared to other additive manufacturing processes, WAM has several advantages as listed here. One of the biggest advantage is the build volume and speed. So big volume, and the volume is almost governed by the reach of the robot. So we can build really large objects, and also the setup is comparatively inexpensive, and also the material cost is relatively cheaper compared to the powder-based power sources. And the wide range of feedstock is also widely available commercially, because all the welding consumable can be used as a consumable for the wire arc additive manufacturing process. So we are using this system, and in the additive manufacturing process and also in the WAM, one of the major drawback is like the continuous columnar grain growth, or the texture, the material shows a strong directional certification. As a result of the directional certification, often the quality or the mechanical performance of the build is poor compared to cast or wrought products. So in this presentation, we'll be focusing on an intermittent deposition strategy through which we will try to control the grain size in WAM process. So for this strategy, basically, during the deposition of the succession layers, we are allowing to cool down the previous layer to an intermittent temperature or interface temperature. We have figured out through our trial and error basis, basically, that 200 of intermittent temperature works best for this attitude, for this approach. And with this intermittent deposition strategy, we are, here is the Ebsd grain maps showing the grain sizes or the grain transition as a result of the intermittent deposition strategy. As you can see, we're working on two materials, stainless steel and Inconel. And in both materials case, you can see that the columnar grains are merging into some sort of like fine equiax grains. So we are saying, or this phenomena is generally called as columnar to equiax transition. And we are seeing that fine grain region for both materials shows almost equiax size morphology, and also the grain size varies between the columnar grain region and the fine grain region. So first thing is, first question comes like where these fine grains are forming, and then how these fine grains are forming in the WAM process with intermittent deposition strategy. So to figure out the location of the fine grain, basically we took hardness plots at a different location across the layer interface, and we found that the region right below a layer interface showing the highest hardness. And also from the grain size maps, we know that there are fine grain regions. So we are relating the high hardness region with the fine grain regions. And from the hardness map, we're relating that the fine grains are forming right below a layer interface. So with the location is cleared out, like the next question comes like why the fine grains are forming right below the layer interface. So to investigate that one, we took the help of the thermal modeling. So we are trying to simulate the temperature thermal history of our deposit. And we are using quite a simplified geometry as a thin wall structure. And we are running a power source, a heat source on the top surface of our structure. And from this thermal simulation, basically, we're recording the temperatures at different location. And based on that temperature, we're doing our further calculations. So from the literatures, one of the things we have found that the ratio of the temperature gradient and the solidification rate is the major factor that has been identified as the major factor to control the columnar to equax transition. So based on in our case, we are using the simulation results or the temperatures from the simulation to calculate the thermal gradient and also the solidification rate. And we have plotted the G by R ratio as function of distance from the top surface of our deposit. And we have found that in the G by R ratio for both material, it shows a decreasing trend from the top, but near about like 3 millimeter from the top surface, there is a sudden decrease in the G by R ratio. And this same phenomena is replicated in both materials cases. And we also found that this 3 millimeter distance is also identical to our layer thickness in our deposits. And based on this G by R ratio found from the simulations, we are correlating basically the high G by R ratio regions with the columnar grain region and the sudden drop of the low G by R ratio region with the equax grain region in our deposits. So with this, we also try to investigate the effect of the grain size heterogeneity into the local deformation behavior. For that, we performed the digital image correlation analysis, and we saw that for both materials case, the local strain and we saw there is a difference of local strain in the tensile test, or under uniaxial tensile test, we saw periodic regions of high and low local strain. And basically with that, we took local strain gauges in fine grain region and columnar grain region. And we found that in both materials case, the fine grain region shows low local strain and also a higher work hardening rate, which we are relating with the Hall patch effect or the grain boundary strengthening because of the grain size in the fine grain region. After figuring out the deformation mechanisms, we are also comparing the results or the mechanical performance with the continuous deposition or continuous columnar growth regions. So basically for both materials case with the intermittent deposition strategy or with the alternating grain size, we achieved an improved mechanical performance in all cases compared to columnar grain growth cases. And this improved mechanical performance, we will be attributing it to one of the thing is the change in microstructural features. And addition to microstructural feature, we are also considering the grain size heterogeneity or the overall smaller grain size with the periodically alternating grain size in our intermittent deposition strategy. So based on these results, we are concluding that through the intermittent deposition strategy, we can achieve microstructural grading in wire additive manufacturing. And also this the microstructural grading is achieved through a columnar to equax transition during the deposition process. And this columnar to equax transition is a result of the local G by R ratio. And also with this approach, we can have improved mechanical performance in the WAM structures. With this, I'd like to thank the support from CMR and our group member for Professor Kim and other group members of the Smart Manufacturing Group. And I would also like to thank Dr. Lee for his support and advice, and also our collaborator at the University of Tennessee. Thank you.
Thank you, Raman. Our next presenter is Cyanide Jadhav from Tennessee Tech University. Fabrication of thin-walled overhead overhang structures using cold metal transfer-based wire and arc additive manufacturing.
Yeah, can you see my screen?
Yes, we can.
So myself, Cyanide Jadhav, I am going to present present the topic that is fabrication of thin-walled overhead and overhead structures using cold metal transfer based wire arc additive manufacturing. My advisor is Dr. Duc Bong Kim. So these are the contents of my presentation: introduction, goal, preliminary investigations, issues, summary, and references. So basically, this figure shows the various types of structures. The first is the overhead wall structure. So here the substrate will be there, and the structure will be deposited in the upside down direction. Then in overhang, you can see this wall will be having at some angle inclined to the horizontal direction or center line of the substrate. Then in overhang direction, the wall will be build direction will be parallel to the horizontal direction, and it will be then in incline wall, you can see the substrate will be horizontal and the wall will be making an angle, and the build direction will be in the vertically upward direction. So these are the some structures which are fabricated at different angles by using metal additive manufacturing. So my main my main focus is to manufacture the overhang overhead structures using the CMT based wire arc additive manufacturing. So in CMT based wire arc additive manufacturing, the cold metal transfer technology is used. So here this slide shows the various forces which are acting during the deposition of incline wall. So major forces which are acting in here are the arc force, droplet impact, gravitational force, and the surface tension force. So arc force mainly dependent upon the current during the deposition process. Then the droplet impact, it is going to depend upon the mass and the velocity of the material. Then in case of for depositing overhead and overhang walls, so here are the different forces that are going to act during that deposition process. So Fs is the surface tension force between the molten metal and the previously deposited layer. Fa is the arc. So here the surface in overhead and overhang structures, the surface tension will be given as Fs is equal to Fm0 As into T minus Tm. So Fs is the surface temperature of metal at a temperature T, and F0 is the Fm0 is the surface temperature of metal at a melting point, and Tm is the melting point of the metal, and As will be the negative of the dFs by Fs by dabba T. So that is the negative temperature gradient of the surface temperature. So now how to deposit this incline walls, overhang wall, and overhead walls. So here this first figure shows the deposition method for depositing the incline wall when the torch is aligned with the incline angle. So here we can for depositing incline wall, you have to move the torch in the after depositing one layer, you have to move the torch in the horizontal as well as in the vertical direction. So that will and that will be giving you alpha inclination angle, and that will be based upon this formula: tan alpha is equal to delta D by delta H. So delta D is the horizontal movement of the or the movement of the torch in Y direction, and delta is the movement of a torch in the Z direction. Then another method is in that the torch is kept perpendicular to the substrate. So in that also we had to move the torch in the horizontal and vertical direction to get required inclination angle alpha. Now in overhang structures, you need to move the torch perpendicular to this plane. So your torch travel direction is this one, and the in the build direction you need to move the torch in the y direction, y direction. Then for overhead walls, you can see the build direction is in downward direction, means you have to we have to move the torch in the downward direction, and molten metal it's flowing down due to the gravity. So while depositing this overhead wall, I use the weaving path. I have given the weaving path to the torch so that the more surface area will be there, and due to that the capacity. Due to that, there will be increase in the capacity of the substrate or the previously deposited layer to hold the molten metal. So here, this is the weaving path. So the various parameters for weaving path, there are weaving amplitude, that is the distance from the center point to the maximum height. Then there are weaving frequency and the dwell time. So dwell time is the time for which the torch is staying extreme points like this and this. That is the time for dwell time is the time for which the torch is remaining for that time. So that may be 0.1 second, 0.5 second, like that. So the goal of our research is to relate the process parameters and the surface roughness based on DOE for overhead and overhead structures, and second goal is to investigate the underlying physics and the process signature, and third goal is to investigate overhang structures of different materials such as the Inconel, low carbon steel, SS316, and the S13 alloy. So for this we use the this setup, the cold metal transfer based WAM system. So it consists of a wire feeder CMT power source, the welding robot, which will be controlled by a robot controller, then the welding table on which the welding substrate will be mounted, then the Miller inside arc agent auto that will be used for acquiring the data such as arc current, arc voltage, and the wire feed rate, etc. Then we have also IR pyrometer that is used for measuring the temperature, and machine vision system. We have a machine vision system to record the videos during the deposition process. We have a HDR camera, then high speed imaging setup, and the thermal imaging setup also. So now I will go through the some incline walls that we have deposited at our lab. So firstly we started with a 30-degree incline wall. So we started with a SS316 316L material, Inconel 625 S13 alloy. So these are the some images, inner and outer surface images of these structures. So here we use the wire feed rate to travel speed ratio of a 9.28. Similarly, we deposited 60-degree incline overhang structures with the same wire feed to travel speed ratio of a 9.28 for these three materials. And we also deposited the 45-degree incline wall for this material. So here we observe that the surface finish of for all these cases, the surface finish of SS316L walls was poorer as compared to the Inconel and S13 alloy. Then we deposited the 0-degree overhang wall of the S13 alloy with the wire feed to travel speed ratio of 9.28. And for depositing overhang wall of Inconel 625, we use the weaving tool path because it was not, we were not able to deposit with the regular tool path. Now after that we started with a deposition of overhead wall. So here we can see the SS overhead wall of SS316L. These are the various deposition parameters with a feed rate started for first layer as a 2.9 and the travel speed of 15. So without we use the weaving tool path, because without weaving, after 2 to 3 layers, their humping defect was forming, and due to that, we were not able to make a wall of good height. So that's why we use the weaving path for tool movement. Then these are the some overhead wall structures of Inconel and H13 alloy. So here the main issue was at the end points, the length of the wall is going to get reduced at layer deposition goes on, or after layer by layer deposition, the length of the wall is going to decrease. Then to investigate this, we recorded the videos. Just sorry, videos are not playing. Yeah. So we observed the process by recording the video during the welding. So it was observed that for Inconel material, the amount of molten metal during the deposition that was higher that as compared to the H13 alloy, and due to that, the Inconel was having more more reduced length at the end. So these are the images which are showing how this issue get accumulated after layer by layer. So at the end, we were able to fabricate the wall of a maximum height of 50 mm and the length at the end of 70 mm by using Inconel material. But the surface finish of the deposited surface finish of the wall was not good. So the issues we are facing in fabricating the overhead walls, that are as the layer by layer deposition proceeds, the thickness of the wall gets reduced, because the molten metal is going to move downward or flow down due to the gravity. And the second issue is the surface finish of the wall. And third issue, that is the reduction in the length of the wall due to the previously deposited due to the flow of the molten metal in the due to the melting of previously deposited layer and backward flow of the molten metal. And the fourth defect, fourth problem that we were facing, that was the formation of humps after 2 to 3 layers. So we are working on this. So the summary of this preliminary investigation is that in case of overhead position, high surface tension force, a larger area of the previously deposited layer helps in placing the molten metal at required position. The surface tension depends upon the temperature of previously deposited layer. So the interpass temperature is important factor in depositing the overhead walls. In overhead wall deposition, we need to take care that the gravity force should always less than the sum of the surface tension force and the arc force. So in order to achieve that, we need to reduce the wire feed rate as the deposition process. So main controlling factor in this deposition are the wire feed rate, travel speed, and the interpass temperature. If we control that 3 parameters, then we will be able to we will be able to deposit wall of a good quality. These are the some references that I use for my presentation and my preliminary investigation. Thank you. Any questions? For any questions, you can contact me on my email ID, that is smaadhav42@tntech.edu. So I will I am very much thankful to organizing committee of AMD for giving me an opportunity to present my preliminary investigation. Thank you very much.
Thank you. Our next presenter is Saiful Islam from Tennessee Tech University. And the presentation is titled Gas Tungsten Arc Welding Based Wire and Arc Additive Manufacturing of Niobium Zirconium 1 Refractory Alloy.
Good afternoon, everybody. Can you see my screen?
Yes, we can.
I'm Saiful Islam. I'm a first year PhD student at Mechanical Department here at Tennessee Tech. My advisor is Dr. Dagbong Kim. And today I'm going to present on gas tungsten arc welding based OEM of niobium zirconium refractory alloy. Generally, the nickel-based super alloys are used for the gas turbine blades, which can operate up to 1600 degrees centigrade, but their development has been plateaued. Thermal efficiency of the gas turbine engines mainly depend on their turbine inlet temperature, which can be increased by around 2% if the operating temperature is increased by 100 degrees centigrade. So higher operating temperature and the reduced rotor weight can result in a better combustion engine efficiency as well as environmental friendliness. So refractory metals and their alloys have much more higher melting temperature, and they can be used and they can retain their strength up to much more higher temperature than the nickel-based alloy. And among the refractory alloy, niobium has the least density, which is around 8.56 gram per centimeter cube. So niobium-based refractory alloy has a great potential to replace the nickel-based super alloys. But one of their major issues is their manufacturability, because generally powder metallurgy or vacuum arc casting are used for the manufacture of the refractory alloy, but they don't provide geometric flexibility and they're semi-finished. Lots of machining need to be done, which results in high buy to fly ratio. With respect to them, metal OEM has lots of advantages like design flexibility, higher energy efficiency, and low material wastage. But the major problem with the OEM is they have different kinds of defects like poor surface finish and lots of porosity and high temperature oxidation with respect to the refractory metal. So our studies focus on the feasibility of the OEM of niobium zirconium refractory alloy and to investigate the correlation among the process, microstructure, and property. So we deposited 3 thin wall of niobium zirconium alloy with GTA-based OEM. We changed the arc current, varying the energy density and heat input. So we deposited 3 wall, and as the heat input increased, our energy density increased, the wall bead width increased, and the wall height decreased some. This is due to the fact that at higher heat input, the molten pool has much more fluidity due to the lower viscosity and surface tension. So after that, we did the microstructural characterization. First, we did the optical microscopy to see the microstructure. The microstructure mainly consists of the columnar dendritic structures, and which is elongated towards the bill direction. This is very much common in case of the OEM component, and we could not find any kinds of cracks or porosity in our structure. And layer interface and interlayer regions could be easily identified in the OEM images, which are shown at higher magnification in the blue and red region. And the layer in the layer interface, there is discontinuity in the dendritic structure. This is maybe due to the partial remelting of the deposited layers. Then we tried to do some EDS to find the elemental distribution of the elements. We did first the area mapping, and then we did the line scanning. In the area mapping, we found that major constituent was niobium, which is more than 95%, with very small traces quantity of zirconium and oxygen. And in the zirconium map, we found that zirconium is mostly present in the interdendritic region. On the contrary, niobium and oxygen both are homogeneously distributed across the microstructure. Then we performed the line scanning map to find if there is any elemental change in the dendritic or interdendritic region. but the line scan showed no major fluctuation in the peak of the pure niobium. Then we did the Ebsd analysis to find the grain morphology. So this shows that in each of the condition, Ebsd map shows very large columnar grains in 3 of the condition. And in case of the Ebsd map, there are in a single grain, the large columnar single grain, each grain consists of multiple columnar subgrains with almost identical orientation. The subgrains could be identified due to the slight mismatch in the color coding, which are shown in the black arrow. And in the IPF map also shows that there is a strong texture in 001 direction, which is common in case of the OEMed component due to the large thermal gradient in the build direction. And after that, we did the Xrd analysis to find the phase continuum if there is any other minor phase apart from the niobium phase. So we found that the major peaks of the Xrd is around 38, 55, 70, and 83. And these peaks correspond to 110, 200, 201, and 220. All are BCC phase according to JC PDS 035 and 0789. And then the calculated lattice parameter was measured at 0.3289, 0.329, and 0.3293 for the low, medium, and high heat input case, which is very closely matches to pure niobium. And the slight change in the lattice mismatch also indicates the solid solution is strengthening, which is the major strengthening mechanism in niobium zirconium 1. And after that, we measured the micro hardness from bottom of the substrate to the top of the deposit at a spacing of 0.5 millimeter. So there is a very increasing trend in the hardness value as the measurement height increased. This may be due to the different microstructural change or due to the dendritic army spacing. There is some drop and peaks in the values. These are due to the layer interface and within the layer when the indentor was there. And average microhardness value in case of the low heat input case was 175.8, and medium heat input case it was 169, and high heat input case it was 191.19 HV. For the mechanical test, we performed the tensile test in each of the condition. We made 4 tensile specimen for each condition. 2 are in vertical and 2 are in the horizontal direction, all according to STM E8 standard. We did the tensile test, but we could not find any correlation in the tensile strength and with respect to the sample orientation as well as the heat input condition. Niobium zirconium is a ductile material. Most of our tensile sample failed in respect to ductile failure, but some of the specimens failed in the brittle failure. This may be due to the impurities in the component. And this is some of the summary of our tensile data with respect to other studies. So in each of the heat input condition, our OEM niobium zirconium has much comparable or better yield UTS and elongation compared to PM and EVM, powder metallurgy and electron beam melting niobium zirconium 1. But with respect to the multi-axial forging and the accumulated roll bonding, our yield stress is much more less. But both of these are SPD or severe plastic deformation techniques. They have very fine grain size. Their strength comes at the expense of their ductility, which can, so we can say that OEM niobium zirconium 1 has the potential to be used with respect to the different in the OEM case. And in our OEM case, the grains are elongated. So the strength mainly comes from the subgrain formation. So the right hand side of the image shows when we took the misorientation line mapping, there are some peaks, smaller peaks in the misorientation. These peaks are maybe due to the subgrain, and these subgrains are responsible for the strength of the WEM niobium zirconium 1. So these are the studies we have done. So that's the end of my presentation, and thank you everyone for your time. And if you have any questions, you can email me. I have given my email here, and I also thank the organization committee to give me the opportunity for my presentation. Have a nice day, everyone.
Thank you. For those of you following on our agenda, we are about 9 minutes behind schedule, but this brings us to our next topic, additive manufacturing from the United Kingdom. And we will be hearing from Alan Rennie of Lancaster University about establishing a design for additive manufacturing research community in the UK.
Thanks, Michelle. Can everybody hear me okay?
Yes, we can.
Excellent. Well, good afternoon to you all, or good evening if you're in Europe or in the UK. It's great to be able to join you for this first in the series of the Additive Manufacturing Days at Tennessee Tech, and long may it continue as well, I hope, year on year. It's been excellent listening in so far. I'm here at the invitation of Professor Fidan to talk about the Design for Additive Manufacturing Network in the UK and how we've gone around establishing that network and using the financial support of the Engineering and Physical Sciences Research Council here in the UK, who are part of UK Research and Innovation, to allow us to pull together a really comprehensive approach to design for AM in the UK. And actually, it's you know, we've capitalised, I think, on COVID over the course of the year or so that the network has been running, and actually gone a lot further than the constraints of the boundaries within the UK, and actually gone quite global, and we'll touch on that as we progress through. I'm also acting on behalf of the principal investigator of the network today, Dr. Patrick Pradell from Loughborough University, who's helped put together some of these slides as well. So without further ado, jump straight in. There we go. The presentations so far today have been excellent, and I think what comes out from a lot of those is the importance of design in the context of additive manufacturing. Much of the research that's been presented has reflected on things like functionality and complex shapes and development on demand properties, and obviously a session or so ago on multi-materials as well, and the properties therein. And we see that reflected in WOLAs as well. The most recent report telling us that there's over $5 billion worth of expenditure on the production of direct use additive manufactured parts. And that's only set to increase year on year as we progress further into the development of the technology, through technology development, through the software developments, through materials developments as well. What I'm here to focus on really is the design aspect, and actually the importance of design for additive manufacturing rather than in additive manufacturing in design. And that generally is application driven. You see on the diagram on the left-hand side there, a number of application or sector areas where additive manufacturing is really coming to the fore. Good examples there for aerospace. Automotive is a good one. The image that you can see in the top left is from Pat Warner from Renault F1, and the use of metallic powder bed fusion to fabricate what is a really complex component there with a number of channels running through them. On the bottom right, for example, in terms of musical instruments, you'll be familiar with the work of Olaf Diegel in New Zealand and his financial ventures through ODD Guitars. Again, design for additive manufacturing plays a huge part there. And I guess over the course of the last 18 to 20 months or so, with the onset of the COVID pandemic as well, much attention paid to things like PPE within our health services and trying to combat the lack of that. Certainly within the UK, there was a big focus on 3D printing and additive manufacturing to try and help boost supply chains at the very start of the pandemic. And you see the image in the top right there from Imperial College in London, and then some stuff I was doing with colleagues in Turkey on that bottom left image around the development of visors as well. And that really is fundamental here, why it's important to have a network such as the DFEM network, because everybody was trying to do their own thing there, and there was no coordination, no approach in how to take forward those that were appropriate through validation and certification processes. So about two and a half years ago, we started to sit and think about what would our vision be for something like a network, and talking with colleagues at Loughborough and at Lancaster and around the UK, coming together with this vision to bring together what we consider to be internationally leading but very disparate research across the UK community, and to try to promote that world leading research that we know we have both nationally in the UK and internationally as well, and to try and bring that together into a coherent single point of access, accessible by other research disciplines, mathematicians, statisticians, material scientists, medics and healthcare providers, all the other research disciplines, and also to try and give a focus towards our governmental agency, our funders as well, and show them actually where research money should be directed, with a focus towards what the UK is obviously keen on developing. That then led to a number of objectives, and I won't read them out verbatim, but they are there for your own perusal. But things like the cooperation and collaboration, coordination between design for additive manufacturing researchers. In the UK, certainly it's very obvious that much time is wasted in the development of research proposals, many of which don't get funded, and that really is wasted time. To be able to bring people together, for example, and come up with a coordinated approach on how to deliver a research agenda was a key thing for us. Looking at the innovative future research challenges, and again, I'll come on to that in a few minutes or so. Again, collaboration, scaling up that research and creating critical mass in key areas. Again, we'll focus on that in a couple of minutes or so, and you'll see some of those key areas that have emerged. Again, collectively speaking to funding bodies and standards agencies. So funding calls will be tailored towards what we believe is fundamental research that needs to be undertaken, with input and collaboration with, for example, our industrial partners. Promote that wider importance of DFEM, and then obviously to leave some legacy afterwards, some sort of sustainability for the network overall. So the model looked a bit like that, a sort of tripartite setup with academia at the heart of that, industry feeding in, and obviously a number of stakeholders that would help us market and benefit and drive some of this forward. And like I say, lots of international interest now as well, so we've included that in our model. UK professional bodies, colleagues that are listening may be familiar with, for example, the Manufacturing Technology Centre in the UK, the professional engineering institutions such as the Institution of Engineering and Technology or the Institution of Mechanical Engineers are all now playing a part into this network, which is great. And our industry engagement is increasing at every event that we have as well. So lots of exciting things going on. The original academic partners there, again, these institutions I'm sure will be familiar to many of you in terms of name. The most proactive, I think, within the UK in terms of additive manufacturing research and engagement and knowledge transfer. So led by Loughborough and Lancaster for this network, but others including Brunel, Nottingham, obviously Sheffield, Leeds, etc. So bringing them together, and we had the support of them to pull together the network and to start to drive this agenda forward. We launched the network on the 6th of November in 2020, right in the middle of what we didn't expect to be was a very long pandemic. So everything started online. But what that allowed us to do was actually bring in international speakers as well, and really bring together an excellent agenda program for that launch event, and really start to create some good dialogue between those that attended. So very rapidly, we decided to hold 2 development workshops at the end of November 2020. And you see on the right-hand side some of the input we had using things like Miro boards from our attendees there to trying to develop what we believed were the key research themes, what's emerging, what needs to be done, both from a academic research point of view, with industrial input and other stakeholders feeding into that process. And that set us forward on a pathway for the development of what we call in the key research themes, the KRTs. So KRT1 was delivered in April 2021, led by Robert Kay from the University of Leeds, looking at the design of the future additive manufactured electronics. Very well attended. In fact, all the KRT events so far. I've had in excess of 250 registrations and probably 60 to 70% conversion on that in terms of attendees. So really rich, valuable events that we've been able to deliver. KRT2 was designed for additive manufacturing for education. Our key research team lead there was Eugene Pei from Brunel University, London. Again, another very excellent event that was delivered. Reports have come from that, and academic papers are on their way. And then most recently, Ajit Panesar from Imperial College London, delivering the computational tools, pushing the frontiers of DFEM. Again, another really excellent event. So our academic participants have grown, as we might have expected. I think we now have over 50 who have registered to be part of the network in some way or other. So alongside our original 11, it's great to be able to get coverage across the UK. But as I said, we've now actually got engagement across the whole of the globe, and we've had attendees come from West Coast US to East Coast Australia, and further, and everywhere in between. So really excellent to see the reach and the engagement that the network's been having. Similarly with industry and research technology participation, we had an original 8 organisations that supported the network with letters of support and in-kind contributions. Sellafield are a large nuclear organisation in the UK. Others that are more familiar, I'm sure, Lego, 3D Systems, Autodesk, etc. So some really prominent additive manufacturing users and original equipment manufacturers and software developers in there. And that's growing as well. I think we're actually heading towards 50 companies overall as well now that are actively engaging within the network. It's not just about academics themselves, but also developing our future researchers and academic colleagues. So we launched a Design for Additive Manufacturing poster competition in 2021. We had 3 prizes given out there, supported through the network and EPSRC's financial grant to us. There was no bias, I promise, towards Hannah Burford from Lancaster University winning first prize. I was completely independent from the process, but well done, Hannah. She's actually won a few awards for her work on that. Second prize went to Justinus from Newcastle University, and then third prize to Charlie Butterworth from Strathclyde. So some really excellent work that came through there. But we want to continue that, and anybody that's listening and is keen to enter, we've got a 2022 DFEM poster competition. And like I say, really to try and support early career researchers and students to adopt design for additive manufacturing principles within their design practice. Rather than give you a very long URL, by all means scan that QR code there. Deadline will be 15th of May, but the theme really is showcasing your DFEM utilizing computational tools for that, and that can feature in many different ways. So please do consider an entry if you're an undergraduate or a postgraduate student working in the area of additive manufacturing. Our next event is in February 2022. It's going to be led by Professors Kenny Delgado from Newcastle University and Professor Richard Bibb from Loughborough University, looking at the design for additive manufacturing in redistributed healthcare. And that's going to be in collaboration with the Redistributed Manufacturing and Healthcare Network. It's another EPSRC supported network. So again, capitalizing on joint working and creating a critical mass in areas that are of relevance to the technology and applications as well. Our online presence, if you wish to follow us, the website designforam.ac.uk, or find us on LinkedIn or on Twitter as well. So the addresses are there. But what we've recently launched, and it'd be great to have you listed on there, is a DFEM network directory. So register yourself in there as an expert. The link is there. And ideally, what we're trying to do is leave a legacy as well, so that anybody that comes to the network and is looking for a collaborator in a particular area can come, they can find somebody, they can talk to them, and the network will help to engender that and really cut out some of the wastage that we see in research funding applications. Find the best people to do the best work with you and take that forward. So again, thank you for the invitation to come and speak today. It's been really great listening to what's going on. I do have another commitment I've got to go to straight after this. So I'm going to miss the last couple of talks, but thank you very much. And the last thing to leave you with, it is St Andrew's Day today. St Andrew is the patron saint of Scotland. So anybody that's out there, have a great St. Andrew's Day. Thank you.
Thank you, Alan. Our next speaker is Robert Bowerman of Autodesk in the UK, and his presentation is titled Multi-Axis Additive Manufacturing with Fusion 360.
Okay, thank you very much for the introduction. Good morning, good afternoon, good evening to everybody, wherever you may be. Thank you for giving me your time to listen to this very short presentation. I'm going to talk about one of our products, which is focused around additive manufacturing, which is Fusion 360. And in particular, I want to talk about some new functionality that we've just launched into that product, which enables users to create multi-axis additive manufacturing toolpaths, which I think would be particularly relevant for some of the talks that I've already seen today. So hopefully there's some good, useful content in there. A very, very brief introduction to myself. My name is Rob Bauman. I'm a technology consultant at Autodesk. I'm based in the UK, I'm based in London, and I work on our Fusion 360 product. In my day-to-day role, I work with customers to try and understand their needs for additive manufacturing and what they're trying to do with the process. And then I work with the development teams to try and implement some of those requirements into our product. So hopefully they can be more successful with the technology. So starting from a slightly higher look, I suppose, of additive at Autodesk, you can really summarize our activities in 4 areas. We have our product offerings. I'm sure you're familiar with Fusion 360, and also our specialist additive product, which is NetFab. We also have a range of technology centers. The technology centers are in-house workshops where we're able to get hands-on with the latest machines and equipment. These are located across North America, and we also have one in the UK. And these are a fantastic location for us to be able to really test out and validate our own software using the latest equipment. But it also gives us a facility in which we can bring customers in, and it's a low-risk environment where they can test our software with the latest equipment, and they can try to realize their design and manufacturing desires using that. We work in a range of collaborative projects that often span multi-years, industrial collaborative projects. We work in these areas to try and push the boundaries of new manufacturing technology, as well as doing our own internal research. We have a large research organization that work on manufacturing projects. That's, as I say, internal, but some research is also undertaken with external partners as well. So I want to focus slightly on one of those products that I've mentioned, that is Fusion 360. Today within the product, you're able to drive 3 main additive processes. Those are fused filament fabrication, stereolithography, and selected laser melting. And to support the selected laser melting capability, we also have process simulation capability, which enables users to see the heat input during the powder bed process, and also the distortion of their parts, which should give them any prior warning to a build failure, be it a support failure or a recoater crash. Now, all of these processes are 3-axis additive processes in their configuration. And I wanted to talk a little bit about some new multi-axis toolpaths that we've implemented into the product. So why is multi-axis additive of interest? Well, as we probably all know, most of the 3D printers that we use day to day are of a 3-axis configuration. This has proven to be extremely accessible, I suppose you could say, in terms of its cost of equipment. And also the ease of use of the equipment. There are also a range of free slicing softwares out there, and the combination of these factors has made the technology flourish over the past decade or so. But obviously with this configuration, there also comes some challenges. We know that we need to support overhanging surfaces. This leads to significant material waste in support structures and also additional post-processing time. We're only able to deposit onto flat surfaces all the build plates that we put into these machines. So that means if we have stock of a different geometry that we wish to deposit onto or add features onto, we're currently not able to do that. And certainly with large scale additive systems, we suffer from the sort of staircase effect on upwards facing surfaces. So multi-axis systems sort of have the ability to overcome some of these problems. And the technology is obviously not new. We've seen multi-axis additive for some time now, predominantly with directed energy deposition technology, as this technology tends to be integrated into more high-end machine tools that have 4- and 5-axis configurations or on robotic platforms. But we are starting to see plastic or concrete systems also make use of this kinematic chain, particularly with robotics. And we're starting to see some lower cost desktop machines also be integrated with 4th and 5th axis. So that's fantastic. It means the hardware is advancing, but we also need software to be able to create the tool paths that can drive these machines in the first place. And software solutions do exist, but we find that the existing solutions on the market are inaccessible in terms of the cost, but also the ease of use. So by bringing some of these toolpathing capabilities to Fusion, we're hoping to overcome some of those hurdles. So what we have done, and this is actually brand new, Fusion updated last night, and these toolpaths went straight in there, is we've created a brand new toolpathing strategy to enable people to deposit onto planar, cylindrical, revolved, and arbitrary surface types. And you can deposit onto these surfaces with a parallel infill pass and a perimeter pass. And this will enable users to build in a 3+2 or synchronized 5-axis motion. And you can also independently control the tool axis of your deposition head aside from the toolpath. And what you can see from those clips on the right-hand side is the toolpath is conformal to that base surface that we've selected. Now, this technology is primarily aimed at driving directed energy deposition machines and hybrid machines, but with some modifications to the post-processor, which is the piece of technology that spits out the machine-specific code. You could also drive other deposition technologies, plastics, concretes, large-scale machines, etc. So I'm telling you this really because I would love you to all go and try it. If you have the need for multi-axis toolpaths, or if you have an installation of Fusion 360, this capability will be available to you today. It's what we call a preview feature, which means that you can turn it on in the preview features panel in Fusion 360. If you are associated with an education institute, Fusion 360 is free for you to use. So these toolpaths will be at no cost to you. And we would love people to go and experiment with them. And we are actively seeking feedback, which can be made through Fusion 360, the feedback hub, or directly to me. You can see my email address there. I realize I've not given any sort of walkthrough of these toolpaths, but if you follow the link that's on the screen there, or you access the help for Fusion, you will see a workflow video which will take you through the entire workflow. So thank you for your time today, and thank you for this opportunity to speak to you. I hope you all enjoy the rest of the presentations.
Thank you, Robert. This brings us to our last topic, which we've called Additive Manufacturing Potpourri. And our next speaker is Andrew Gothard of Tennessee Tech University. His presentation is towards dynamic characterization of fully 3D printed capacitive sensors for footbed pressure sensing applications.
Hello, as she said before, my name is Andrew Gothard and I'm a master's student here at Tennessee Tech. And today I'll be presenting actually some of my undergraduate research that I did here at TTU on the dynamic characterization of fully 3D printed capacitive sensors for footbed pressure sensing applications. And my advisor on this work was Dr. Stephen Anton. So to begin, I want to talk a little bit about the motivation for this work, specifically a medical application called gait analysis. And so gait analysis is the study of forces and kinematics behind human locomotion. And you can see the typical gait cycle of a human in this top right-hand corner here. And so pretty much everybody knows someone who's undergone some kind of orthopedic surgery, such as a knee or hip replacement, and has struggled with their movement, or knows somebody with some kind of deformity, such as having club feet or even flat feet. And so gait analysis is a tool that's used to help orthopedic doctors to assess the outcome of these surgeries and identify these neurological and musculoskeletal disorders. And so one of the key tools used in gait analysis is called a footbed pressure mapping. And an example of this for a typical gait cycle can be seen here in this animation. And so an orthopedic doctor will normally bring in a patient and then gather this footbed pressure data and then assess it in order to help them make the diagnosis for a patient. And so a simple example would be for them to observe if the patient is flat-footed or not. Normally, how this data is gathered is through gait laboratories, as seen here. And the problem with these gait laboratories is often these patients have a hard time moving or getting around, hence the need for these gait tests. And so bringing a patient into these gait laboratories and having them walk around for several hours can put high amounts of strain on patients, especially if they're elderly. And so there's been a shift towards using pressure sensing insoles, where the patient can simply put these insoles inside of their shoe and then transmit data wirelessly back to the doctor. The problem with this type of insole, though, is they're rather expensive and not customizable. And so you can see here, if you tried to trim these sensors, you would actually end up breaking the circuit. And also these kind of insoles are not customizable for shape. So someone with like club feet couldn't use these insoles. So the idea behind this project is being able to scan a patient's foot and then create a customized pressure sensing insole in order for them to be able to get the pressure distribution map for their orthopedic doctor. And so some previous work that's been done in this area, first is by Lee et al., who developed some conductive carbon-based filament for pressure sensing applications and was able to apply this for finger pressures. Valentine et al. Took a similar but slightly different approach by printing a flexible TPU matrix on an insole and then using a pick and place machine to place commercial capacitive sensors into this matrix to sense pressures. While this could customize for size, it couldn't customize the shape of the insole. And Xiao et al., who was able to 3D print a fully TPU capacitive sensor, but these sensors were only tested at lower frequencies of 0.2 hertz and showed considerable amounts of drift. So for this work, we focused on developing fully 3D printed capacitive sensors made out of conductive PLA and then non-conductive flexible TPU, and then dynamically characterizing those sensors using a compressive load frame at various frequencies and pressure levels. And then we evaluated how well these sensors were able to track the dynamic changes in pressure and quantify the amount of nonlinearity we expected to see in these sensors. So first, for our sensor development, we use an Ultimaker S5 printer and went through an iterative process, and we found these parameters here in this right table. The most important of which to pay attention to is that 10% infill. And we used a lower infill percentage to help increase the sensitivity of our sensor, but found that anything lower than 10% actually reduced the quality of our sensor. So that's what we maintained it at. Once we created our sensor, we then tested it on a Newton resource load frame at load levels of 25, 35, 55, and 75 Newton per centimeter squared. It should be noted that typically for an adult, the pressure level is between 0 and 35 Newton per centimeter squared. Our sensors weren't quite sensitive enough to hit those lowest load levels. So instead, we tested at some of the higher pressure levels in order to better characterize the sensors. And then we tested at frequencies of 1, 3, 5, and 7 hertz, which is typical for gait analysis. And in order to actually capture the signal, we used a capacitance to voltage converting circuit from SingleTAC and a NI DAC card running LabVIEW. Once we captured the signal, we smoothed the curves using a moving average filter. And for each of the tests, we ran a 30-second test for each of the load levels and frequencies. And for each of those, we knew we wanted to assess the nonlinearity and get a calibration curve. So we extracted a single peak after the signal had stabilized to look at the calibration curve of those. What we found was that the sensor was able to track the load levels and frequencies reasonably well. However, we did notice that there was variability in these signals. So we decided that these shorter 30-second tests were inadequate to determine the variability of the sensor. And also we wanted to be able to quantify the nonlinearity. So in order to do this, we ran a longer 1-hour test at 35 Newton per centimeter squared. And we found from this test that there was a larger amount of variability than we had first expected. And so we found that was on the order of 38%. And then on the positive note, though, we did find that there was no deterministic drift in our sensor system. Looking at the calibration curves and the nonlinearity for our sensors, it was highly nonlinear as expected from the materials. However, we wanted to quantify this, so we fit a linear model to each of these and calculated both the hysteresis and linearity errors and found them to be a maximum of 68.9 and 34.9% respectively. So overall for this project, we were able to create the flexible conductive PLA and TPU capacitor sensors and evaluate them at pressure levels between 25 and 75 Newton per centimeter squared and frequencies from 1 to 7 hertz, and found that they were able to track these dynamic changes in pressure with no deterministic drift. But we did see a high amount of variability on the order of 38% and a high amount of nonlinearity with hysteresis on the order of 68.9 and linearity error 34.9%. Moving forward, we began testing and developing nonlinear models to help with the sensor's prediction output. And also we've been moving towards printing multiple sensors to determine the statistical repeatability for these sensors, and then test for things like infill density and infill geometry and its relationship to the sensor sensitivity. And then finally, in order to get to that goal pressure range of 0 to 35 Newton per centimeter squared, we are testing different filament types to see if we can get a lower modulus to help increase the sensitivity of our sensor. And so thank you, that's my work. If you have any questions, feel free to email me at this email. Thanks.
Thank you, Andrew. Before we hear from our last presenter, I'd like to remind you again about the question and answer form that is in the chat. Mohammed has been posting that regularly, and we will leave that up for a few minutes after our last speaker, who is Tyler Stanifer and Daniel Vandenberg from Tennessee Tech University. And the talk is titled Creation of a 3D Printed Tactile Learning Device with Embedded Fiber Optic Sensing.
Can you hear us and see our screen?
Yes, we can.
All right. Good afternoon. My name is Dr. Dan Vandenberg. I'm in the Department of Civil Engineering here at Tennessee Tech, and I'm joined by Tyler Stanifer, one of our undergraduate students who worked this past summer on creating a 3D printed tactile learning device with embedded fiber optic sensing. So we're going to share with you a little bit about our process here. So the motivation for this work has to do with the fact that engineering students in mechanics classrooms, which we have here in civil engineering and in mechanical engineering, work with very abstract and difficult to understand concepts and ideas. So going from what we can draw on paper with a simple beam with a load on it, producing stress there on the left. What we wanted to do was to develop a tactile hands-on learning device that would help students understand those ideas. And so the process that Tyler is going to share with you about is how do we develop this and create the beam that you see shown here, as well as the support structure for this device. And one of the key components to this is the fact that we embedded fiber optic sensing technology within the 3D printed structure. If you're not familiar, fiber optic sensing can be used to obtain distributed strain measurements in real time. And so some of the equipment we used was the Odyssey interrogators from Luna, along with their optical fiber shown on the right. So essentially the size of human hair, much smaller than a foil strain gauge or even, you know, a dime. And the advantage of this strain technology is that it provides strain measurements along the entire length of the fiber, not just one location. And so just as an example of what that might look like, you could see along the length of the fiber, which is the x-axis on the screen or on the plot shown here, we could obtain strain measurements at small increments on the order of 1 millimeter with this system. So now Tyler's going to describe how he went about the design process.
So with the beam dimensions, we decided to go with 18 inches for a couple of reasons. We wanted, one, for students to be able to see this clearly, so we didn't want it to be too small. And then also with the Luna equipment, with the strain sensors, the smallest sensor they have is a 1 meter fiber. So we needed it to be big enough so we could get the entire fiber into or embedded into the beam. So with the depth, it was also dependent on the bend radius of the beam or of the sensor. So it has specific bend radius, so we needed to make sure that it was large enough to accommodate that sensor. With the material, we also wanted a low stiffness we wanted the strain to be able to be seen clearly. So students looking at it, if it's too stiff, it's not going to show very much. And so we wanted the strain just to be substantial under these small loads. And then we also went with a W-shaped beam, also known as an I-beam, just because it's something that students are familiar with in these mechanics classes. They see it quite often. So we wanted it to be recognizable. So with the material selection, we chose PETG material. PLA is very commonly used, and it's good for most applications. But for our project, it would just probably be too stiff. So we decided that PETG was going to have a good combination of that strength and flexibility to get that strain, like I previously said. And then we used MakerBot and Stacker printers. We had one vertical print and one horizontal print. The MakerBot we use vertically, and the Stacker we use horizontally. Most 3D printers have really small bed dimensions in terms of what we're looking for. So going vertically was pretty much our only option in a lot of ways. So the picture on the right is it printed vertically. That's what we did in the printer. We did it normally without any of that support, but it ended up failing. So we had to add support to the middle of it and then at the bottom so that it wouldn't fail as it got taller. So with the support structure, we used this beam mount, and it can do a pinned and a fixed connection. So the beam would go into the top part of that beam mount, and that would be a pinned. It would be pinned right there, and then on the right is the roller. So you could actually have a pinned and roller set up, and then you could take it out and you could put it in the bottom one, and that would be fixed. So you can get different setups so you can see strain in different ways. And then for the beam mount, we decided with PLA because it is that stiffer. It's stiffer than PETG, so we wanted it to be stronger. We didn't want any skewed values in the strain. So when we load the beam, we didn't want it to be somehow skewed because it's the same material. So we just wanted something that was stronger than the beam itself, or more stiffer rather. And then with the printing orientation, we wanted it to be in the most cost-effective way. So the bottom figures on the right show how it's oriented on the printer. Obviously, if we had printed those vertically, we would have had way more support, and it would have ended up being a lot more filament to use. So we just kept that in mind when we were printing. So the left figure is the CAD file with the groove layout. So this was actually drawn up in SolidWorks, and this was where the fiber would go. So that way we can get a precise location of the fiber and know exactly where it's at in the beam. And then on the right is the two vertically oriented half sections of the beam that were actually clamped together, and then we glued them and then basically welded them together with the same filament so that it was one solid piece. The picture on the left is the horizontally printed. This is on the stacker, and you can see where the fiber is. Essentially how we bonded this was we took some excess filament and we used hot iron. So we laid the sensor in there and we basically just welded the sensor into the beam. So it was one solid piece and it wasn't going to move. It was going to move with the beam. Unfortunately, on the horizontal, it did not complete very well. It kind of failed, but we know it's possible to do horizontal because we would lay this down, we embed the sensor, and then we'd essentially just continue the print right on top of that. And it did start working, but we ran into some printer issues, whether that be from the printer or the material. And then the right just shows the fixed and pin beam support that I talked about previously.
Now we're going to show you just a few results of the beam in action. This first one is just going to be a video. There's no sound. I'll talk about it a little bit as we go. It's not perfectly synced, but I think you'll get the idea. The top left figure is going to be that part of the sensor is along the top of the beam, and then the bottom graph is going to show you the strain along the bottom of the beam. So we're going to put a weight on here, and you can see the top go into compression, the bottom into tension. And as we move it around, we get immediate response of the strain within that beam. I could take it back off and then see the, again, the compression zone at the top and the tension zone at the bottom. A few other examples of just still shots are this one here, where we've got the beam in the moment connection configuration. So along the top of the beam, which is the left part of the strain plot, we've got the highest strain at the connection, going down to 0 at the tip. And then it curls around to the bottom of the beam and the strain increases again back to the connection point. And then the last part of the sensor was embedded at the neutral axis, and you see we have essentially 0 strain there. Then just another configuration. Here's a still shot of the beam and sensor in the simply supported mode with our load at the middle of the beam causing compression at the top and tension at the bottom, and again 0 strain along the neutral axis.
So just to summarize, just what we had talked about, we had manufacturing challenges. So obviously with the vertical print, when it get really tall, it's hard to maintain the alignment. So that was an issue that we had found. We worked around it by adding supports. With the horizontal print, obviously the size of the printing bed is sort of an issue since most are not as big as what we were needing them to be. We also found that the PETG tended to clog more, especially with the stacker printers. And then it just ultimately ended up being unsuccessful. But we know it is possible to do a horizontal print. It's just overcoming those challenges. And then the fiber optic installation was actually probably the easiest part of the project. Actually getting it in there was seamless. It worked really well, and good bonds were maintained in the project. And then we obviously wanted students to visualize and interact with this strain. So it's pretty easy setup. You can actually take it into a classroom and set it up really easily and quickly. And then, yeah, having these just in mechanics and structural engineering classrooms just to help them really see what strain is and to understand it. And then so for future work, we would want to retry the horizontal print. Like I said, we know it's possible. So getting that would be something we would do. And then we'd study the impact on student learning, if this is helping students to actually see what's going on, if they understand it better. I'd like to say just a special thank you to Kyle Wendt and Robert Shelton, as well as David Bradford, for their help and their input in this project, as well as the SCI program through Tennessee Tech, because that was where this undergraduate research was done.
Thank you.
Thank you to the presenters and to the attendees for your attention. Lastly, I will turn it over to Ying Zhang Director of the Center for Manufacturing Research at Tennessee Tech, who will make some closing remarks.
Thank you, Michelle. I would like to thank Sorry. Okay. I would like to thank you all for participating in today's event, especially to all the speakers. You did a wonderful job. And I would like to thank the meeting organizers, particularly Dr. Fidan, for leading this effort. And last, I really appreciate Michelle's help, who she made today's event, seamless. Just thank you all, and I look forward to seeing you again next time. Bye.